Okay, thank you for reminding me. I start recordings for every class, but I forgot to start it for my own. So yeah, we didn't mismatch. As I said, we are just going to cover the class data storage and management, the basic information on how data is stored and managed, from the basics to the more advanced presentations. I will just tell you, so I have the chat open. I am generally pretty relaxed lecturer, so feel free to ask me questions, interject. If you want to turn on your mic and ask, if you want to ask me in chat, go ahead. It's really not a problem. This is more theory-based class, so we won't have any exercises or anything like that. So feel free to join in the class through questions and similar. Okay, so what are the actual topics that we are going to be covering here? We are going to go from basic data types, the media that the data is stored, and file systems. This is what I plan on covering in today's class. We'll also cover data redundancy, data transfer protocols, and basic databases in following classes. And at the end, unstructured data, and we will provide with an overview of what cloud services are, what cloud services exist, and etc. So for today's class, we'll focus on these first three topics: basic data types, data storage, and file systems. As you can see, these are the topics that cover the base of how data is stored in the computers. So let's start with that. Let's start with the basic data types. So why are we addressing them? Well, when we are accessing the computers, we're accessing the information in computers. Data is stored usually as binary data in the computer, and there are a lot of different ways we can store the data. And once we read the data, when we get those ones and zeros, we can interpret them in many different ways depending on what we are doing. So based on that, we'll go over how the data is actually stored, some basic terms that are used here, and how data is interpreted by the computers or programs and operating systems that present them to us as humans, so we could manipulate them and understand them, extract information from them. So the starting information is bits, bytes. You probably heard about these terms, unless you are, I don't know which backgrounds all of you have. I know we have a lot of different backgrounds here. If you are in some sort of computer engineering or informatics, you are familiar with this. Even if you aren't, you may have heard bits and bytes as terms. Maybe you have heard about gigabytes when it comes to your computer memory or buying a USB stick or an external hard drive. So let's briefly discuss about what these are, what these values are. So one bit of data is a binary digit that can take one or two values. This is called a bit, basically, because it's a bit of data, just a single piece of information. This comes basically from having a transistor that can be set to a certain voltage in our computers. It doesn't have to be electrical, it can be magnetic, it can be optical, but basically there is something or there isn't something. You can think of it like having a box, and if you put something in that box, if you put some water or a rock in that box, that's a one. If there isn't anything, there's a zero. Why do we have binary system? Why do we have binary digits instead of having decade? For example, like we use in our everyday communication, we use a decade system that has digits from 0 to 9. It's basically for simplicity. To encode something like that, there are systems that existed using them. For example, there are some systems that use a trinary value where you have -1, 0, and 1 to encode it. And all the Russian computers actually use the decade system where they had 10 different levels because that's what humans use, right? The problem with this is that it can be very hard to differentiate between these values because how it actually works with electronics. I'm going to use the basic electronics. Is that the 0 is going to be certain expected values, so 0 volts, for example, and 1 will be represented by usually 5 volts, 3.3 volts, 12 volts, 24 volts, or any standard value. In real world, this isn't always the case. You won't have always exactly 0 volts or 1 volt. You will have some noise, some electronic leakage, etc. So 0, for example, if you're using a 5 volt system, 0 will be everything from 0 to 2 volts, and 1 will be anything from 3 to 5 volts, with the values in between being undetermined. We'll say, okay, we aren't sure here because maybe we have some voltage loss or some extra voltage coming in here that we don't want to. If you are trying to do something like that with 10 values, in an area of like 0 to 5 volts, now you suddenly don't have like a 2 volts of space that defines a 0 or a 1. You suddenly have 0.5 volts, and it's much harder to be that precise. So essentially the reason why we are using these values, so the reason why we are using a 0 or 1 to represent this information is basically it's much simpler for us to develop a system that stores data in a binary form. So representing a value with just 0 or 1 isn't very practical for us. You can't do much with that. So what we do is we group them, and the first grouping of these bits to represent a bigger value, bigger something that has more meaning to us is a byte, and that is 8 bits. So something like 111000 or any combination of 8 bits is going to be called a byte. And this is something, if you aren't familiar with computers, that you have probably heard in terms of kilobytes, megabytes, etc. And so on. We can represent even larger amounts of data with exponential values, but we will talk about this when we talk about IEEE 754. Before we move on, as I said, you probably, if you aren't into computer science and data science and connected disciplines, you probably haven't heard about bits and bytes, but you may have heard about megabytes or megabits for your internet transfer, or you've heard about gigabytes for your phone storage, etc. So we are essentially, because bytes are in today's world very small amount of data, we are using these larger representations that basically use this SI system multiplicators to represent them. So a kilobyte is going to be 1000 bytes, megabyte is going to be 1 million bytes, gigabyte 1 billion bytes, etc. Today we have it's common for us to have terabytes even in regular use. For example, my computer has 2 terabytes of a hard drive in them. If we are talking about servers, petabytes are normal. It's not uncommon to find petabyte servers if they're dedicated to larger data storage. So we're talking about trillion, quadrillion when we're talking about terabytes or petabytes, and even larger like exabytes or zettabytes exist when we're talking about amount of data that large data centers can store. So this is when we enter into that domain of big data, when manipulating that starts to get much harder. And if that's one of the courses you selected, we will talk about that when you come to that class. So one of the things I would like to maybe ask you, maybe let's see if anyone is listening. Has anyone of you ever noticed that maybe when you buy a 500 gigabyte drive or something like that, you connect it and it shows a smaller amount of data. It shows that you have, I don't know, 480 gigabytes or something like that. Does anyone know why that happens? No?
Can you
Okay.
repeat it, please?
Okay, so when you buy, for example, a hard drive that has like 500 gigabytes of data, usually when you plug it in, you will see that your computer won't show you 500 gigabytes, it's going to show you something like 480 gigabytes or something like that. Does anyone know why that happens? No? Okay. Well, the reason why it happens is because there are two standards of showing it. So I mentioned that you have kilobytes before, and 1 kilobyte is 1000 bytes. In addition to that, you have kibibytes. You may have heard somewhere someone say that, okay, a single, so 1000 bytes is a kilobyte, but you may have heard that 1024 bytes is a kilobyte. This is the difference between kilo and kibi. A kilobyte will have 1000, kibibyte will have 1024. Same goes for megabytes. A megabyte will have 1000 kilobytes, but a megabyte will have 1024 kilobytes. This is the reason why we have these differences between when you are actually plugging, for example, you buy a hard disk, a hard drive, you plug it in, and you have a difference in value. It can be because of file systems as well. We will discuss this, but essentially two standards exist. So if you ever see something like kilobytes, that is usually used when you are expressing storage device capabilities. So for example, if you are buying a USB drive or if you're buying a phone, you'll get something like you will get kilobytes, megabytes, or gigabytes used, usually gigabytes or terabytes these days. The reason for that is it's very simple. It's basically for marketing purposes because you get more kilobytes than kilobytes in the same amount of data. It's as computer scientists, we prefer using kilobytes, which is 1024 bytes. This allows us to do some easier splitting when it comes to binary computing because 1024 bytes is 2 to the power of 10. So we can more easily perform certain operations in memory when we are using this sort of grouping of bytes. And that's why you will sometimes see this I entered between K, or this can be, as I said, this can be M for megabyte or G for gigabit. Gigabit. This I indicates that it uses 1024 of the lower unit instead of 1000. Just in case you run into it and you need this information in certain context. Again, with big data and large data storages of today, this isn't necessarily that important. This is usually important when we are talking about low-level stuff such as file system storage and file system operations, programming at a low level. So when I say low level in computer programming, it doesn't mean simple. It means how far away we are from the hardware. So when you say use something like low-level programming language or low-level access, it refers to being close to the hardware and, for example, accessing memory directly, as you can do with C or an assembly programming language. And in those cases, usually kilobytes or megabytes will be used to refer to larger amounts of data, relatively larger amounts of data. So this is just a piece of information for you to have in case you see it somewhere. Okay, so now let's talk about how are we actually storing numbers in the we are actually storing numbers in the computers. Why am I focusing on numbers when we can store a lot of different information? Well, all or most information is encoded as numbers in computers. So all the pictures, images, videos, whatever you have on your data, this actual presentation that I'm holding, my voice is all encoded as a number and then sent. There are a lot of different standards. Just letting you know that this IEEE 754 standard that I'm going to talk about now isn't the be-all end-all, but it's the most commonly used and it's the most widely used. And the other standards that do exist are similar to it in a way. So I just want to demonstrate it to you, just so you know how the numbers are actually stored. Okay, so why do we have different side? Why can't we just write down something like, for example, if we have, let's start first, in case you don't know about binary number representation, we can convert between different number systems. The one that we use is a decade system, and it's based basically the value of something like, I'm going to write it in chat. If you have something like 32, it's going to be written as something like this. I'm actually going to use 232. I made a mistake. Let me just correct it. So, so just so you can understand me better, something like 232 in our, everyday decade system that when we are talking, we are essentially saying we have 2 times 100, 30 times 3 times 10, and 2 times 1. And that is the total amount that we have. We are multiplying the hundreds with the number that's in the hundreds position. We are multiplying tens with the number that's in third position, and so on. Basically, we can do the same thing with binary numbers. So if we have something like this, we have 1 0 1 0. That's going to be 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 1. Okay, so it essentially we can take all the values that are 1 and multiply them by 2 to the power of the position it is. So moving from the back, from the right side, it's a 0, then we have 1, then we have 0, then we have 1, and we multiply it with 0 with 2 to the power of 0, which is 1, and so on. So we can write numbers down. Essentially, you don't need to know this by heart for this class, but what I'm trying to essentially show you is that you can write down a number, even a decimal number, using this system that you have here. So we can, so for example, this number that I showed you is number 10 in a binary system. Why? Because we have the first one equals 2 to the power of 3, that is 8, and this one here, yeah. So essentially you would get number 10 shown like this. But why aren't we just drawing the numbers like this? Well, if I wanted to write down a really, really large number, I want to write down something like 10 million or 15 million, I would need a lot of digits, a lot of binary digits, and I would fill up my memory very fast doing this. So we are going to use floating point arithmetic. What does floating point arithmetic mean? It means that basically the floating point number, so that's the decimal sign. I don't know where you are from, you're either using a decimal comma or a decimal point. It varies between countries, but essentially floating point means that that point is floating. It can be adjusted based on the exponent. So, for example, something like this, 10,000 can be written like 1 times 10 to the power 4. And essentially we have moved, or to illustrate it better, 1.0 times 10 to the power 4. Essentially we have moved this floating point from all the way back to the to the start of the number, and it essentially by moving it we have managed to shorten it and shorten its representation. So now we can, instead of storing this one number, which in 10,000 it would be it would take a lot of points, and by saying a lot of digits I mean a lot of bits to store a single number. We can store two separate numbers, 1.0, so we can store that with 1 bit, and 4, which we can store with 2 bits, and just indicate, hey, this is my main part of the number, and this is my exponent. And this will allow us to store data much more densely. It will allow us to have a common standard on how to do it, and that's basically what IEEE 754 standard is, essentially just a little bit better. So we are talking about taking a number, whatever it is, no matter how large it is or how small it is, converting it to scientific notation. For example, we have 1.6 e simply means 10 to the power of whatever follows after it. If you're using Python, you can use this manner with e to write small or large numbers. Just a hint, because I know that you're using Python for some classes. So 1.6 to the power of minus 19, or 2.22 times 10 to the power of 24, that's mass of the sun. You essentially have really large numbers shown very densely, very simply. You don't need a lot of numbers, so we don't have to have 2 and then 24 zeros to represent this. We can show it very concisely by just converting it to scientific notation. So how are we going to actually store either of these numbers? Well, first we need to decide how many bits are we going to use per number. Usually you will hear something like single precision, double precision. If you are an engineer, maybe you heard about single or double precision when it comes to your SolidWorks or something like that, a engineering software, something like, oh, SolidWorks actually uses double precision so you can represent things more precisely. Or if you are, for example, in graphics design, some standards for illustrating, for storing colors can use 64 bits instead of 32 bits to have a wider range of colors and a more realistic representation. Usually, this simply means that double precision numbers are going to be will allow you to store not only a larger number, but it will allow you to store a number more precisely. That means you can use more decimal points to indicate how precise that number is. So how are we actually going to encode them using this? Well, we have certain parts to this IEEE 754 representation. There are 3 main bits. First is a sign bit that shows us whether the number is positive or negative. It can be simply 1 or 0. Number is positive, number is negative. When we interpret it, we're going to add a minus or not in front of it, depending on whether it's positive or negative, right? Exponent it just includes the scale of the number, so the number that the exponent that we have, so 1 to 10 to the power of the 4, that 4 is going to be the exponent, and the mantissa is more significant. Mantissa is a more commonly used word. It's basically that main part of the number. So let's take a look at an example. Before I look at the example, let me just note that there are certain special values and rounding here that happens. So for example, you have special representation when it comes to infinity, not a number, and the 0. but is there a special representation for a 0, because 0 can just be shown as 0.00 with the exponent of 0 or an exponent really? Well, it simplifies things, because you can store 0 with different values. So 0 multiplying any 10 to the power any exponent will equal 0, so you can store it in different ways. You usually don't want that. It can cause some problems with interpretation. For example, if you decide to be funny and use 10 to the power of 420 to represent times 0 to represent a 0, someone else takes your code and decides to just check whether the exponent is 0. For 0, it can cause issues and so on. So we have a special representation for that, that not only makes sure that 0 is represented equally across all use cases, but also uses less data, because it's not uncommon to store zeros. When you look at data sets, if you, for example, sign up for practical data collection class, we will talk about data sets and how zeros are very, very common in a lot of data sets outside. So simplifying the 0, even if it doesn't seem like very important, now when you have a lot of them at a very, very large storage scales, can actually help to save some data. And this actually helps handle exceptional cases in computation. If you ever heard maybe the term dividing by 0 as an error state, old computers, basically what happens when you divide by 0, the value tends, mathematically we're talking, it's undefined. But if you try dividing by 0, like using, by hand, basically on pen and paper, or if you try using limits or something, you will see that the values grow very rapidly as you are approaching 0. And this causes a lot of issues for computers. Basically, in the early days of computation, it wasn't uncommon for the chips to literally explode. You can find examples of this on YouTube, or for mechanical computation devices that were used before computers. They can simply get stuck in an infinite loop or even break, uh, because the values keep increasing so rapidly when you get the computer to try dividing by 0. So it's much easier for us to simply call this value none, not a number. It's essentially short for, hey, this isn't something that we can represent as a number. We aren't sure what the value is, or what the value should be, so we are just going to tell it not a number. And this can happen if you, for example, have a data set. If I recall correctly from what the colleagues told me, you have in other classes, you have used Python to load data. You have probably used pandas to load some data. If pandas is very good at handling different values and different things. If you try to use something simpler like NumPy and try to load something that's not a number, it's going to throw a fit, is going to be confused, it is going to throw an error because it expects a number and doesn't know how to encode it into the memory. And finally, you have, as I mentioned, infinity, in case it's usually written as INF or infinity. I'm going to again write it down in chat just so you can see more clear what I'm talking about. This is usually the way infinity is encoded, and usually some operations that tend to infinity, I used 0, dividing by 0 as an example. Again, I know mathematically speaking, it's not tending to infinity, it's undefined. But in computer science, we like to simplify that and just be like, oh no, dividing by 0 is infinity. And a lot of modern programming systems will just return you an infinity value if it detects, or not a number value if it detects that you have tried dividing by 0 somewhere. Finally, you will see that we can't necessarily always encode every possible number, and we sometimes need to round the number to show it, because we have a limited amount. As I said, we have 32 bytes or 64 bits, I apologize, bits to store these values. So we are going to, if we are storing something that doesn't fit there, we need to round this. And there are different rounding modes for this, whether we're going to round to the nearest number, we're going to use essentially the floor function and round down, or we're going to use ceiling and round up. Usually it doesn't really matter unless you are doing something really precise, but yes, rounding can cause errors, and float and double can cause errors. So we'll see how actually this works. So let's see basically the encoding of a very simple number. So let's say you want to save something like 3.0, very simple single digit number in your computer. How that is going to be? So if you open your Python and you write something like a equals 3.0, this is what essentially happens when this value is stored. So first, that 3.0 is converted to binary and scientific notation. So 1.1 times 2 to the power of -1. Okay, that was the first step. I'm not going to enter in how to exactly convert binary numbers. It's base level math. You can easily look it up online, and a lot of programs allow you to automatically convert this. It's a very common operation. So the first thing that we're talking about is the sign bit. We have the positive. So we're going to use 0 for positive, 1 for negative. Why is it like this? It was basically how the standard was written, how it's defined. 0 means a plus, 1 means a negative. It has something to do with how electrical charges are defined, etc. But I want them to, it's beyond the scope of this lecture to essentially go into the history of defining the standard. Then the exponent that we have here, 1 is going to be encoded, so we're going to add it to 127 and represent it as a binary. So this is the step we are essentially adding 127 to it. Finally, the fractional part of 1 is 1, and since this is 1, we are simply padding it to 23 bits, so we are adding the 22 remaining bits. And finally, we combine this. So we have the exponent, the sign, the exponent, and the mantissa. That's the order where it's on how it's stored. Again, this is something that you will necessarily need to know to code. We are just illustrating that storing the values of numbers within computers isn't as straightforward and as simple as you want to. And you can, this is important to know, not necessarily how to convert individual numbers, but what you need to know here is essentially, hey, the representation isn't that simple. There are possible errors, there are possible issues with this. It has happened to me in the past. I have converted a value, so I had a code for calculating, modeling a certain phenomena that was written in Pascal by an older professor. And to basically use that with the remaining code base, we needed to convert it to Python. And what happened to me is I converted the code. I fixed all the errors. I adjusted all the calculations so it would be possible in Python, because there are some differences usually between programming languages that are more than skin deep. And essentially, I had an automatic checker to see if I get the same results, and I wasn't getting the same results. And I spent like a week breaking my head trying to figure out what's the problem, only to figure out that the problem is that the default precision for a floating point number is single. So it's 32 bits in Pascal, and it's double in Python, so it uses 64 bits. So my results were more precise, and as I was iterating and repeating this calculation, I ended up getting slightly different final results for this location, this output that I was getting from the software, than I was getting in Pascal. They were essentially the same, just more precise. And when I was comparing them one-to-one programmatically, I didn't notice that. So yes, this is something that can actually cause you a problem, because storing a number in not just between different programming languages, but between different operating systems or different computers. Whether we are using a 32-bit operating system or versus a 64-bit operating system, which are the most commonly used today, you can get different results with the exactly same code. So that's something to look out for, because it's one of those things that you forget until it essentially bites you and causes you a lot of headache trying to figure out why aren't the values what you expect it to be. Okay, in addition to this, something that you will commonly see when we are talking about storing values in computers are hexadecimal numbers. So as we used base 10 for decade system that we use in everyday life, we mentioned binary that uses 2 as the base. We also have 16, and essentially this is simply used for brevity. And if you ever encounter a number we want, again, at this level that this class and this course is meant to teach you, we aren't going to go into in depth about this, but essentially if you ever encounter a value that has 0x at the start, this is a hexadecimal representation. And one thing that this means, usually when you have when you see these types of values, it usually means memory, whether it's RAM, whether it's direct hard drive. If you ever encounter the term hex dump simply means all the memory values of the program placed in a text file. So this is something that you may encounter sometimes. We just want at this level for you to be familiar with the fact that these are hexadecimal numbers, and these usually in computer science represent some sort of a memory, some sort of a value that was stored somewhere. So going on, all of these that I mentioned are stuff that you usually don't see. Now, when it comes to programming, I know you already had last week the programming introduction to programming for data science and artificial intelligence. We are now slowly going to enter the level of data representation that has something to do with that, that you may have used there. So we are going from that low level to higher and higher levels. And these are basically basic data types. What does basic data types tell? What do these data types tell us? What do they serve for? Well, if you have something like this, you have this number stored 3.0 or any number stored in the computer. The way you interpret it, if you have a program and you write something like print that variable, what that value that your computer is going to show you depends on how you are going to interpret these ones and zeros, and how we are interpreting them is essentially data types. So what are these most common data types? We have integer, which shows whole numbers, so 1, 2, 3, 4, 5, 6. This says, so for all of this, they say typically 4 bytes, usually 8 bytes. If you're programming something like Python, this doesn't matter. If you are doing something more precise, if you're using something like C or C++ as a programming language, be careful. Never assume that a certain data type is a certain size in bytes. So this means, for example, integer will usually get represented by 4 bytes, which means 4 times 8, 32 bits. This isn't always the case. It can be 16, it can be 8, it can be, there are different essentially values to this. Most programming languages for default will enable you to get the value of this. For example, in C, you can type in something like size of int, and it's going to return you the exact size of that data type on your computer, on your on your operating system, whatever you're using. So the hard code this and never assume, oh, hey, this is 4 bytes when it can actually try to get that value programmatically through coding. In addition to integer, for storing whole numbers, usually have something like long and short that stores larger integers or smaller integers. So using 8 bytes, also as I said, that's 128 bits, or 2 bytes, so that's 16 bits inside. Again, modern applications usually don't care. Python doesn't even, it allows you to use all of these, but it doesn't really show it to you as an option. You can just type in a equals 4, a equals 5, and it's going to figure it out for you. But if you're doing something that's more data sensitive, maybe you are programming some portable system and you don't have a lot of memory on it or something like that, you can use short to store numbers so you don't waste memory if you don't need anything larger. This isn't necessary today, and which isn't necessarily great. A lot of programmers and system engineers argue that this isn't really great because a lot of people tend to default and say, like, oh, let's just use long for everything. We have a lot of storage, and that's why a lot of programs today and data today is simply blown bigger than it should be because everyone is using, people aren't paying attention to essentially which data types they are using, and this causes bloat in essentially file sizes and code sizes everywhere. So yeah, you should have a certain degree of balance what you're using. So if you're ever coding something, try not to contribute to this problem. Try to figure out what you need to use. In addition to this, we have here char. Essentially, char or a character represents a single character. When we say character, we mean something like A, B, C, D, right? For example, letters. Space, backspace, anything like that, that can cause essentially that can represent any sort of a character single, whether it's for example enter, carriage, return. There are a lot of different examples. When you put characters together, you get a string, so that's a sequence of characters. For example, any of your names, first and last names, your mail addresses, anything like that is a string. And then we get to basically float. You remember from before, I talked about floating point representation, or essentially about floating point, basically how floating point numbers or decimal numbers are stored. So we have float and double. That is essentially what I mentioned. Float uses usually 32 bits, and double usually uses 64 bits, or in other words, as it says on the screen, 4 bytes or 8 bytes. Again, what should you use? What do you need? That depends essentially on your needs. You don't always need to default to using double. You can sometimes use float, it's good enough for you. And finally, one important data type is a list or an array. They aren't the same thing. I know that if some of you are computer engineers or computer scientists, you know very well that a list and the queue and an array and the vector aren't the same object. But again, for the purpose of this class, this is more of an introductory class. Any sort of collection of elements that are given in a certain order They are called a list or an array of data. And this is something that's very, very commonly used in programming. And the list can usually consist of any of the other data types. You can have a list of integers, list of floats, list of doubles. String is essentially a list of characters. Some programming languages will allow you to mix different values in the lists, etc. They're very, very useful and very, very commonly used. As I mentioned again before, actual sizes will vary from system to system, from computer to computer. It is usually determined by your CPU and your operating system. In addition to that, as I said before, interpretation of data is based on data type. So, for example, in C, a character is an int displayed as a letter. This simply means that if you define something that both character and an integer are stored in the memory in the same way, if you store in the memory something like a value of 44, and you say, okay, I want to see that value as an integer, is going to return to you 44. If you try to say, okay, let me see that value, the same memory value as a character, a letter, is going to return to you a capital letter A, despite it being the same value. So you can sometimes even misinterpret data if you aren't careful about data types. To avoid issues with this and to try fight that bloating problem that I mentioned previously, modern programming languages usually avoid this and basically tell you, hey, you just store whatever you want in the memory, and I'm going to figure out what data type this is, whether this is going to be. So, for example, if you create in Python a variable that's called the name, and then you can store into it your name as a string. You can store into it a number. You can store into it a ton of different values. A floating point number, an integer, you can overload it and essentially convert integer to floating point or vice versa, all within the same variable. These programming languages that allow you to do this are usually called dynamically typed languages because they have dynamic data types, and the data type of a certain variable can switch between different types. In older programming languages or more strictly typed programming languages, you can do this. You can't, if you say that something, that the variable A is an integer, it is going to stay an integer. Even if you want to convert it, you have to create a different variable that is a float if you want to convert that integer into a float or vice versa. Basically, that covers essentially the data types and storage, so the base level of storage of computers, of data in computers. Before I move on to the next topic, I'm just going to ask if there are any questions regarding this previous part. If there are, feel free to type them in the chat, raise your hand, whatever. I'm going to give you just a few seconds to see if anyone starts typing, starts talking. No, okay. I'm going to move on to the second topic of today. As I said, I want to ideally cover the initial three topics today before we, so we can essentially have the base knowledge about data types going forward. So the thing I'm going to cover now is data storage media. So we're going to discuss the different types of media devices that you can store digital data. Again, focusing on this is an introductory class. We aren't going to go into like hardcore engineering, but the idea is to introduce you to what exists. You're probably familiar with most, if not all of them, and just discuss where to use which data type, what are some advantages or disadvantages of different data types, and how to select them based on their speed, capacity, cost, durability, etc., which to use as your primary storage that you are working off of, and which to use, for example, secondary, tertiary storage, which are just things you are storing in the background, maybe your backups or something like that. So let's start with data types, with media, data storage media types. First, let's talk about factors that we have here. So we have the performance, and usually we are talking about this speed for read-write operations. This speed will usually, you will have two ways this is expressed. One is in operations per second or access per second. This is usually done for RAM for your computer, so the memory your computer is using while it's running, or is going to be given in megabytes per second for secondary storage, such as hard drives, USB sticks, etc. The capacity, again, is the amount of data you can actually store there. Today, usually we are talking about megabytes at the worst, gigabytes, usually terabytes, or I think terabytes are the most a single piece of hardware can store at this point, at least that I know of. Finally, we have cost, which is usually expressed when we are talking about a large storage, and in computer engineering, we are usually talking about not the cost of a unit, we are talking about cost per gigabyte. How cheaply can I purchase a gigabyte of storage? And finally, the reliability itself, or how individual media, without any additional techniques that we are also going to discuss, is resistant to losing data. So let's go into the classification. We have primary, secondary, and tertiary storage. Primary storage, as I mentioned, is the storage your computer is using right now. When I say computer, I'm using that very liberally. So your phone, your tablet, your laptop, your computer, your mainframe, whatever you are currently using. To write this, for example, this stream right now, when it comes to you, is stored in the primary storage, is stored in the CPU cache. It's stored into the random access memory, RAM, that your computer is using. These are high-speed memories that allow you to actually, in real time, as I'm talking, process this, display this, display the stream I'm sending of the video stream that is being sent here. That's all stored into your RAM as it's shown to you. Volatile simply means that if you run out of electricity, you shut down your computer, this isn't stored. So this stream, unless you save it, right, unless you download the video afterwards, isn't going to be by default stored because RAM would lose, right, that information. Secondary storage is usually non-volatile data that's slower than the primary storage. So we're talking about hard disk drives, solid-state drives, or flash drives. Tertiary storage usually refers to the types of data that you aren't using constantly. So, for example, a hard disk drive or SSD is something that your operating system has information on, that you have information on, that you're currently working, your documents, and similar. The stuff that you aren't currently working on, maybe that you're backing up or storing or something like that, that's tertiary storage. And finally, just an addendum to this classical three tiers of storage, you have cloud storage, that's remote storage. It's nothing like there's this common joke that cloud is just someone else's computer. We're going to talk about cloud and how it's accessed and protocols on how to transfer the data later on in this class. But essentially, it's someone else's computer that you are storing data on through internet, right? Whether you're using, for example, Google Drive, it's just a server that's somewhere that you can access or the internet and put the data on and download the data off of. So let's start talking about different types of actual storage devices that are in use today, more or less popular. I'm not going to talk about like floppy drives and stuff like that because we aren't using them anymore, so I won't even mention them. Hard disk drives aren't that commonly used today. Most of you right now probably only have SSDs in your or other flash-based storage in your phones and so on. Basically, hard disk drives look a bit like this. They're a bit bulkier. The most common diameter for this disk that you see in the center is 3.5 inches or 2.5 inches. And essentially, these discs that you see in the middle are magnetic. They will spin, and here you have the read-write head that will either be used as a sensor and read the value that's stored there, whether a certain sector is magnetized or not magnetized. If that should remind you of what I talked before about bits, whether there is electricity or not, whether it's a box where there's water in it or not. Instead of electricity, we are using magnetism here. So whether a certain sector, a certain small section of this drive is magnetized or not is going to indicate to us whether the value is 1 or 0. The file is stored essentially in this in a circular motion on it, circular fashion on it, and as this spindle, this center disk spins, is going to come under this read-write head, which can move radially, so from the center of the drive to the outside of the drive, and that will allow you to basically read information of this entire. So this head will move from the center to the outer rim to give you a full coverage, and the disk itself will spin. You can see on this example you have multiple individual heads. Essentially, this reading arm has multiple instances for multiple disks. This is essentially vertical hard disk where it stores. Most hard disks of today are like this because there's what defines how much data you can store on a hard disk. Well, it's how precisely you can modify individual sectors, and that depends on the material you are using for the actual disk, and how precisely you can actually rotate both the head and the spindle, the central disks. And you have a limit to this, and this limit basically defines how many bits you can store on this entire data. So if you can calculate it. If you have a 0.01 degree rotation, you can calculate how many individual data points you can have on the disk. So to increase that, people started stacking multiple of these disks, essentially one on top of each other, into a single enclosure. What are the problems with hard disk drives? Well, they are mechanical, and that this will be the problem because the motors can give out. If you bump a hard drive, if you ever had the great dissatisfaction as I had multiple times of hard disk drive, external hard disk drive, dropping off the floor, hitting the ground, it can completely destroy it to the point it's unusable. There are some techniques that you can actually freeze it and hope that, because it's mechanical, as basically the mechanism contracts when you put it in your freezer, and usually wrap it in something so it doesn't get condensation on it. It might snap back into place and you can get the data off of it. Maybe it doesn't always work, but yeah, so it is problematic. And not only you might say, okay, great, but we are talking about servers. We are talking about a computer where the hard disk drive, is going to get dropped on the floor. It's stored in a server in a computer chassis, is safe. We don't have to worry about it. Well, when you have a lot of drives, the vibrations. So you have, for example, one of the servers that we have here, you have, let me see, 6 times 24, 28 hard drives in it, and you can have in a single rack, in a single enclosure, you have maybe 10 of those drives. You have 280 drives, and the vibrations of the surrounding hard disk drives can actually damage the hard disk drives, so they can actually destroy themselves when you have a lot of them working together. Modern hard drives try to avoid this, essentially with using rubber gaskets and basically uh, mounting these arms and platters on different spring mechanisms to essentially try to not destroy themselves, because essentially hard disk drives are either used in relatively cheap modern electronics, like maybe if you get a cheap laptop or a cheap computer, relatively cheap, you will have a hard disk drive in it, or they are used in where a lot of data is needed to be accessed directly through computer, because they're cheaper than SSDs. But yeah, modern hard disk drives try to affect this, but they will usually last not as long as other storage devices. Even modern ones will have tendency to destroy themselves in a couple of years, especially if you're using them in a modern computer data center environment where there are hundreds of them in enclosures working 24/7, because you are essentially having a bunch of spindles working together, vibrating. And once they fail, they tend to fail catastrophically, and it's almost possible to get data of them. So those are the issues that we have generally moved from hard disk drives to flash storage. Flash storage. Actually, a lot of students actually ask me when we are talking about storage, does this have to do with like a flash player that was popular in the past? No, it's a different thing, so don't confuse it. But basically, it's storage based on chips, electronic chips such as this. So essentially, your USB drive, your SD cards that you may have in your phones, there or just generally, even if your phone doesn't support SD cards, its memory is usually stored in an SD card that's just soldered on top of your mainboard. Essentially, these are electronics that basically use really small transistors. And transistors, I mentioned them before, are simply an uh, electronic operator, an electronic element that allows you to store a 1 or a 0 on it. So they are, if you work with transistors as hobbies, they will be in a size of about your thumbnail or your pinky nail, while the actual transistors that are used, when you are creating them with modern processes, are much smaller, and you can store millions of them in a relatively small space, and basically allow for storing a lot of data on a relatively small space. So SD cards today grow up to 256 gigabyte. I've seen even 1 terabyte, 1 terabytes SD cards in use today. So that's, you can store a lot of data on a very small small piece of physically small piece of equipment. So basically, what are the benefits of this flash storage? Well, uh, it's not mechanical. That's the main thing about it. You essentially you don't have to worry about vibration. You don't have to worry about any of those issues that I mentioned with hard disks. They actually require less power, which isn't something to scoff at when we're talking about hundreds or thousands or millions of drives. And you can store a lot of data on them. They have a high data density, which means that you can have a lot of data in a relatively small space. Uh, they aren't without their issues. Essentially, writing and rewriting cycles, due to how everything is set up physically in flash storage, can destroy the storage itself. So they have a limited lifespan, a limited amount of a limited amount of read-write cycles that you can do to them. So if you plug in your USB drive, if you still carry one of those, I do, and just start writing data to it, it's going to eventually just fail because the material basically at hardware level just gives out like it did with hard drives, but it's going to take a lot more in professional environments. For most of us, this isn't going to be a problem, right? When we're talking about flash storage in modern computers, we are usually going to use the term SSDs. These are essentially flash storage. This is essentially flash storage that's shaped in the form of a hard disk drive that you can plug into the computer and use in the same way that you would use your hard disk drive. They take up less space, they use less energy, but they also have that problem that, well, they can fail after a while. Again, for most of us, this isn't going to be a problem. We're talking about really, we're talking, especially with modern SSDs, a lot of read and writes before they physically fail. But in addition to them physically failing, a lot of these drives today use different smart technologies like load balancing. So they won't always write if you have multiple chips, like you see on this Micron 7450. You want to use the first chip to store the data always. The data will be stored on different chips to get it balanced, to get the wear balanced. In addition to that, if you buy something like a 500 gigabyte drive and it's a really good drive, you might be actually buying a larger drive, something like 1 terabyte or 750 gigabytes, because it's designed so in case if it fails, if you lose one sector, right? If you use a few million of those transistors that I mentioned, you lose one chip, it's just going to write data to a different section, right? It's going to basically using the controller on them is going to figure out like, okay, this section is starting to fail. I'm going to need to write the data, just silently copy the data to a different sector and forget writing to this damaged sector. This is something that's not exposed to you. If it happens to you, you will never know it. It's handled directly by the drive. So that's something that is basically done to address those issues of solid state drives. Uh, Essentially, as I mentioned, SSDs are electronics. We are going to go back to, well, magnets. Why are magnets so interesting to us? Well, basically, magnets were what was initially used to store information because it's very simple, like magnetizing and demagnetizing media that can be magnetized, steel or whatever it is used. It's very simple to do with a decent amount of precision. So that's why in older days, I don't believe anyone listening to this is old enough to remember when the cassettes were used for audio or for video, and the reason for that is these cassettes were very simple. You could have a relatively simple read and write head that's going to magnetize or demagnetize basically a strip of plastic that has some metal inside it that can be magnetized, and basically based on the direction of magnetization, you can have a 1 or 0 stored or an analog value stored. You can store a lot of data, so that density basically for magnet storage is going to always be higher than electronic storage. As I mentioned, hard disk drives have a higher density than SSDs, and they are cheaper than SSDs because they all that smart things about sector balancing and checking the health of the individual sectors. You don't need to do any of that, so it's much cheaper, much simpler to build a hard disk drive than it is an SSD. simple is being a relative term here. Obviously, none of us are going to do it in our basement, but you might actually get like you could build a tape storage in your basement, but hard disk drive or an SSD you simply couldn't. But at a factory level, at that level of processing, building an HDD is much simpler than building an SSD, and that's why it's cheaper even to these days. So what happens when you want more storage? Well, we're going to use something that's called tapes. This is different than the old VHAs or audio tapes that I mentioned that were used to store audio or video back in the day. And they're different than floppy disks that most of you might only know as the save icon. What essentially this does is it stores those ones and zeros that I mentioned are stored sequentially on this tape here. And when you want to access the piece of data, uh, this whole spool will rotate to the point, right? It will unspool until you get to the point that where the data that you want is stored, and you will read that data. That sounds slow, and it is very slow. You can't run your computer. You can't run anything off of magnetic tape data, despite the fact that they will store petabytes of data. They will store so an order above what you can store with hard disk drives or SSDs. You can store with magnetic tape. A lot of data centers use this, but they use them for archival storage. For example, CERN with data for a Large Hadron Collider is stored on magnetic tapes. Why? Because you don't need it, right? You don't need to access it immediately. You may need it, for posterity if there's some physicist that decides like, oh, hey, let me see. I think I may have noticed something, 5 years ago on this date, and then you can grab the tape out of storage and use it, and you can store a lot of data on it, but you won't use it normally. And you will usually have to magnetic tapes come with a digital essentially catalog that tells you where the information is stored on the tape itself, so you can roll to that point and read it. And they are very cheap for storing a lot of data, but very, very slow. And usually, as I said, you need a specialized, well, you need specialized drive for anything. But what do I mean by specialized drive here on this slide? I mean that simply you can plug in your hard disk in your computer. If you want to replace it with an SSD, you can. They use the same interface, SATA. There are some specific interfaces for SSDs, but if you have a somewhat modern motherboard, you don't have to worry about it. You can just buy a drive and throw it in your computer. You can do that with magnetic tapes. You have to buy a specialized drive for reading magnetic tapes. In addition to that, you need to have a specialized software that basically allows you to index where something is on a tape, and getting some data of the tape could take you something like 10 or 15 minutes to read like a video you stored on it or something. So they aren't really popular for use at level of that we are at when you want to back up something, but for large scale archival storage, they are used. Another fun benefit of these devices is that they are very rugged, they're very durable, and that allows for a few kind of fun properties. For example, this will survive earthquakes and stuff like that. Hard disk drives won't. SSDs may survive an earthquake, like just hardware-wise to the design, but they could crack. If you drop section of building on them, these have there are special magnetic tapes that are designed to withstand anything, because you can make this casing out of some really strong materials, and that's basically what's protecting the data inside. So a lot of banks that want to store their data very securely, no matter come hell or high tide, will buy these drives, and you can actually throw them underwater. You can pour sand in them, which isn't the problem because you can just unspool them, wash them off, spool them back in, and put them in a reader. The second thing with this is basically if we go back, you can see that you have, for example, the connection for SSD is going to be something like this. This is for the PCIe or M.2 connection, or something like this for SATA connection. In the middle, these these are basically pretty fine, pretty specific. You can easily break them if you put too much force in. You don't have to worry with magnetic tape storage. They are usually manipulated with robots. For example, I mentioned CERN before. They actually have, you can easily find it on YouTube. If you're interested, just type it in. They actually have industrial robots that will, when you tell them like, oh, I need like, I don't know, 17th November of 2020, the robot knows where that storage is, where that tape is stored, and is going to grab it and put it in a drive for you to read off of, because they can be, you aren't worried about being too fine with them. They're extremely durable. They're essentially apocalypse proof. So a lot of very important data today is stored on magnetic tape storage, despite the fact that most of us won't really use them in day-to-day life. Okay, some other storage types that exist. This that you already may remember seeing are basically optical storage media, wherein instead of using magnetism or electricity, you use light to store bits on them. They are non-volatile, so you can permanently store data on them, and they have a very long shelf life if you store them properly. They are sensitive to humidity or exposure to light. Their capacity is very limited, and writing or rewriting on them isn't necessarily always possible. So that essentially means that once you write data on it, that's the data that's on it. You can't rewrite it. You can store something else. This is why they were commonly used for music or movies, stuff like that. Essentially, that once you put a movie on it, you don't need to rewrite it. You don't need to store something else on it. But today they aren't really commonly used. They're mostly used by, for media storage. Compact discs, CDs are used for audio, DVDs and Blu-rays are used for video. It's not extremely common. Most people today just will stream. I think that most of you, if I put a poll in or something, are going to tell me that you prefer streaming to using anything like this, but they still do exist, and some organizations still use them for storage, mostly because of legacy. Like, we have used this for storage for so long, we don't have time to invest into essentially adjusting our protocols and getting all the data off of these Blu-rays, because we have tens of thousands of them, and it will take us 2 years to just get all the data onto hard drives. So we're just going to continue using this until we're simply forced to change due to the circumstances that we are in. One organization that I'm a part of was in this conundrum. Essentially, what we do, we are called the Global Meteor Network, and essentially what we do is we have cameras monitoring the skies and detecting falling stars, meteors that happen in the atmosphere, and then doing a lot of calculations, determining orbits. A part of the problem that we had, essentially, why is this important? It's because any space flight that you have, from SpaceX missions that are modern today to old space shuttle missions, to just satellites that you use for your TV or for your communication, you need to know when you're launching them, is there going to be a lot of meteors flying around, because you can actually greatly damage your equipment if something hits it. So it's something of great interest, and we actually collaborate with NASA on this. And I had a big problem. We had a big problem where essentially all of our data for years and years back was stored on DVDs, and I was one of the people who had that unlucky opportunity of actually grabbing a bunch of these DVD drives, hundreds, thousands of them, and slowly and methodically going through each one and just pasting it, entering it into a computer and copy pasting a few hundred megabytes of data at a time to a hard drive so it can be uploaded somewhere. So we can actually share that all the historic data, uh, because the organization itself existed since early 2000s. So yeah, usually that's just an anecdote, but essentially optical storage media isn't very commonly used today. Again, unless we're talking about some organizations that exist for a while and didn't really need to switch, or they simply for large collections of digital media in the sense of like videos or music. So let's talk about something that I mentioned a couple of times already now, and that's RAM. RAM stands for Random Access Memory, and it's basically the one of the main memories that your computer uses while it's operating. So right now, depending on your system and what you're trying to do, you can actually don't actually do it, but you can actually unplug your SSD from the computer, and your computer won't shut it down if you take away its drive, because a lot of it is stored in a lot of stuff is stored in the RAM, and it's directly accessed by your computer. Uh, the main benefit of RAM is that it's fast, but again, it's volatile. So once you shut it off, you can't save it, and it's suitable, for storing temporary files. You can actually create something that's called a RAM disk. We're going to talk about this when we talk about file systems, but you can actually create a hard drive, a virtual hard drive that exists in your RAM. Obviously, your RAM is going to be much smaller in capacity compared to your hard disk drive. For example, on this computer, I think I have 4 terabyte hard disk drive, 2 terabyte SSD, and 32 gigs of RAM. So it's an order of magnitude below what I'm actually using, gigabytes versus terabytes on my other drives. So you don't necessarily want to use it for daily operation, but you can use it. To if you need something that needs to be processed very fast and essentially stored as you would store on hard drive, which I essentially mean you can open the computer, my computer, and drag information, drag files to it. You can actually set that up. But it's not very commonly used for obvious reasons. Usually SSDs are fast enough. That was a much more commonly used technique back in the day, when the difference between how fast the RAM is versus how fast your hard disk drive is was extreme. It was extremely significant. Today, it's not that significant. There is, the difference between an SSD and RAM isn't that great. So we don't necessarily get that much benefit from creating a RAM disk. And this is what RAM essentially looks like. It's usually, if you have a standard tower computer, it's usually plugged in somewhere near your CPU. And this is also flash memory, so it's these chips that you see on here. That's what you use to store data with transistors. They are architecturally obviously different to SSDs and different, and use USB drive or SD card, but in essence they are in basic principle they're the same thing, just structured a bit differently to allow faster access to data, so your computer can function faster. Another term that needs to be mentioned is something that came here of, and it's called ROM or read-only memory. This is essentially, it's very similar, it's flash storage that's very similar to RAM, but it is persistent. So once you write data to it, if there is no power, you lose electricity, is going to store data on it. One of the examples on this, on your computer or your phone, you have a small patch of ROM you can access directly, but it's used to store a lot of information about your computer. One of the examples, if you are a bit of if you're more of a computer nerd and you ever played around with your settings, if you're accessing BIOS is written to ROM in part. Basically, the basic software that runs your BIOS is written in ROM. More simple example, if you aren't a computer nerd that likes playing with some special settings of your computer, is essentially your time. So basically, the current date and time is stored in ROM. So once you boot up your computer, even if it's not connected to the internet, it's going to know what time it was when it's stored and what time currently is, so it can show you the correct clock. And there are some more advanced storage structures. For example, persistent memory essentially combines certain features of RAM and SSDs. Practically speaking, for us, the end users, this is essentially much faster SSD. It uses essentially RAM architecture, but in a much more denser way that enables you to get faster access to information and lower latency. Speed and latency aren't necessarily the same. Latency refers to essentially the time it takes you to get. So imagine it like this: latency means that the speed is when I'm getting the data and I'm already reading the data. I can read it at a certain speed. So, for example, let's say if I'm reading a book versus reading a comic book, right? I can read a comic book much faster because it's pictures and not a lot of text, so I can read 100 pages in an hour, right? If I'm reading a book, a standard like novel, it's going to take me maybe 2 hours to read 100 pages. So that's the difference in speed. So in this example, PMM or RAM would be essentially a comic book. It's much faster at getting me some amount of information than SSD, which is a novel, and HDD would be like an old scroll that I need to read through to get information off of. What is latency? Latency is directly connected to speed, because I can have something that's high speed, like a comic book, can be placed at a library, and it's going to take me time to get there. And once I get to it, once I get that initial bit of information, I can read through it very fast, but there is latency in delivery because I need to go to the library to read it. While, in some cases, it might be faster for me to read a novel, right, a normal book, which is at my home because I don't have to go to the library. And this is why currently the fastest type of memory that you have is actually located physically right next to your CPU. It's called cache. And this cache, usually if you're ever buying a CPU, is going to be listed as you will have level 1, level 2, and level 3 cache, which is basically level 1 will be maybe, some kilobytes, then level 2 and level 3 will be megabytes of memory. Why? Because it's really, really close physically. It's right next to like the chip or of your central processing unit that does all the calculations for your computer. This memory is right next to it, and that's low latency memory. It's very fast to access this memory, and the memory itself is very fast. So essentially, that is the difference between latency and, if you see that term, like I mentioned here, the difference between latency and speed. Latency is how quickly you can access the data, and speed is how quickly you can read the data once you have access to it. So that's one example. And cache is something that, as I mentioned, is just normal flash memory that's located very close to your CPU. So it would have both quick read of flash memory, but also low latency. Uh, Persistent memory is something that people are currently working on developing, and it's essentially trying to combine the best of both worlds. So it's trying to have low latency and higher capacities and higher read speeds that SSDs have. So essentially, what you could see through in this topic that I discussed, you have a ton of different data storage media types. So you can store uh, data in many different ways, on many different cases. Don't assume that, okay, I don't need this. But basically, what I wanted to show is don't something that I hear a lot is, oh, you don't need hard disk drives today. You're just going to use flash storage. You're just going to use SSDs. This isn't true. A lot of massive companies like Google and Amazon use hard disk drives today. Why? Because at a large scale, it's much cheaper to use hard disk drives. A lot of massive companies, such as Sony or Disney, that develop like media, right, use optical storage because for their purposes it's better because it has higher fidelity. That's something that I didn't really enter to because it's not really important to us at this level. Uh, there are a lot of what I want you to remember and take away with you from here is that essentially different types of storage exist because there are different needs. No type of storage is necessarily a direct upgrade. Even, for example, I mentioned PMM, persistent memory, that is being developed when it comes. A lot of people right now, in circles connected to the computer storage and data. It's always going to like we aren't going to use SSDs anymore because we'll have PMM. That's not true because PMM is going to have certain problems. If nothing else, at the start, it's going to have, despite very high performance, it's going to be very costly and it's going to be much more practical to use SSDs for us for a long time before we can use this. We can like default everything to PMM, and by the time we have defaulted most structures to PMM, like we have today, dedicated most of our memory in day-to-day use in laptops and phones and computers to flash storage. By that time, the next technology for data storage is probably going to emerge that is going to have different benefits. And despite all of this evolving landscape that we have in data storage, we are still, at a certain level, we are still using magnetic storage, which was the initial storage that was used when first computers were developed in 50s. Uh, right. The only thing that we have really abandoned is using like the punctured paper that was used for storage, on the first mainframes, simply because uh, it's really not usable for us anymore. But even like really old technologies like magnetic storage do have their place today in today's world, not because if they're applied appropriately, right? So that's something that you need to take away with you. That I hope you will understand it. Basically, like if you're ever doing anything regarding like data storage and similar, please remember that there are these elements. Please remember this, when you are selecting data, although you will probably 99% of the cases today going to select flash memory as the default. Just load the SSDs if you can afford them. If you need more storage at low price, we're going to choose hard disk drives. That's basically what happens. And just to mention one thing that I didn't mention, there are hybrid storage types that are basically using caching. Essentially, you can have an HDD which is combined with a smaller SSD, and basically your computer, your CPU or a drive or separate like a small microcomputer on that hard drive will basically tell you, okay, so this person is most commonly accessing this piece of information. I'm going to store that on a faster storage. So you have your hard disk drives, and let's say like here at work, I commonly use SolidWorks to design things. So that hard disk drive is going to detect that and say, okay, instead of storing this 30 gigabytes of SolidWorks on my hard disk, I'm going to automatically move it to SSD and basically use it there. That's also that's something that usually happens today. There isn't a lot of benefit in using that SSD combination with hard disk drives, simply because SSDs are cheap enough that you don't need that. But it was very, very popular when SSDs were relatively new and very expensive for daily use. So that's something that is a trend that usually happens with computers, with new emerging storage technologies. Again, I mentioned PMEM, so I wouldn't be surprised if in the future we had some sort of combination where we had an SSD with PMEM cache that is going to allow you faster access. There are a lot of technologies that I didn't mention, like Intel Octane storage and similar. Essentially, most of the storage types that you see are specialized flash memory. So if I haven't mentioned it here, 90% of the cases, it's some relatively exotic application of flash storage that that has been applied for a specific use case. Like I mentioned, Intel Optane. Intel Optane was used for caching, like I mentioned, for hard disk drives. Uh, okay, and final conclusion here is essentially what actually dictates what type of storage are you using tends to be the amount of money that you have. If you ask me as a computer engineer, I would say like, oh, just use SSDs. If you ask my manager, my boss, he will say, no, 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 like we don't need SSDs here. These data sets that we aren't actually using, actually training models on, they can be stored on hard disk drives, right? And we can save a bunch of money by buying 100 terabytes of hard disk drives instead of buying 100 terabytes of SSDs. We can buy 20 terabytes of SSDs and 80 terabytes of hard disk drives. If we're talking about much larger amount of data, we're talking petabytes, then hey, maybe we can buy uh, maybe we can buy I apologize. Maybe we can buy invest into a tape storage. So the tape storage can be actually used to offset that, and long term, despite us investing into drives and the storage system and everything, is going to be cheaper for us to essentially run that data, store it on the tapes, because tapes are by themselves tips by themselves are relatively cheap. They aren't extremely expensive. The initial investment of getting the drives and the software is what's problematic. Okay, so the final topic that I want to discuss today is essentially that I mentioned, like we want to cover three topics. That's the third topic is essentially file systems, right? We want to discuss what file systems are, how they are used, and etc. So I'm essentially going to start with this, unless I'm just going to give you like 30 seconds or a minute to see if someone raises their hand or starts talking or typing, in case you have any questions regarding the storage media uh, and so. Okay, as I can see that there are no questions here regarding this previous part. I didn't mention it before, but obviously I'm going to post my contact here at the end of the lecture, right, in chat. But if you have any questions or anything, you can also reach out to me. Like, I'm the main administrator for the WSET email, so you can just contact me there if that's simple for you. So let's start with file systems. What are file systems? What are they used for? And what's the point of them? What different file systems exist, etc. Essentially, when you store data on your hard disk drive, SSD, whatever you're using, whichever storage way that you're using, this needs to be organized somehow, right? Because if I just write a number 3.0 to my hard drive, I won't be able to find it later on, right? I don't know where I've written it, how I've written it. I talk about data interpretation, right? Data type. So I have that 3.0 written using that IEEE 754 standard, but I don't know if that's meant to be a double or a float, or it's meant to be a character or a part of the string, right? I don't know what it is. So I need to have something that's going to manage how that data is stored and organized, and it's going to define how I'm going to access it and retrieve it. Then on top of that, if I have already a system like this, it's going to allow me to make sure that that data has integrity, essentially that that data is safe, that it hasn't failed, and it's going to allow me base level of security. We aren't talking about cybersecurity or anything like that here. We are talking about essentially we are talking about not cybersecurity, but like a basic level, access control that you have here, like can I access this file or not. And it's basically a layer of that separates you and the hard drive, that separates you from those ones and zeros, because if you have like, your favorite song and you want to access it on your PC, you don't want that to be a string of ones and zeros straight to you. You want a song, right? So that's going to allow you to basically, when your media player, you double click on the song, is going to enable your media player to be like, okay, this piece of these ones and zeros that are stored at this part of this hard drive is a song. Feel free to interpret them in that way that is going to make music. So that's what basically the file system does. And that's basically that abstraction layer that is going to enable you, that I mentioned, that you don't need to know what IEEE 754 is. You don't need to know what integer float is. This is all managed by file systems. Essentially, it's, it also, when I say manages physical storage, it takes care of you where your data is placed, how it's organized. When you delete the data, it takes care of removing it. When you create a new file, it takes care of reserving, area for that file. When it modifies a file, it allows you to rewrite that file. It tracks how full your hard drive is, so you don't go overboard, don't overwrite any information that you want, etc. That's basically, when I'm mentioning like overwriting, if you ever, go shop on some of those like kind of awkward sites, or you can even see it on Amazon, you can find stuff like 4 terabyte USB drive, or 20 terabyte SD card for some really, joking amount of money, like 5 cents or $2 or something like that. And you basically get the card, you put it in your computer, and it reads as, oh, this has 20 gigabytes, 20 terabytes, on, your basic USB flash storage. So that's achieved with file systems, and essentially lies to the file system to misinterpret the data. It's a common scam. So be careful if you're buying something like that. Use your brain. So let's talk about different types of file systems that exist. You have disk-based file systems that are basically created to address hard drives. When we use the term disk in general, it can be a CD, it can be a DVD, right? But usually in context of computer science, disk means hard disk drive, and there are file systems like NTFS and Ext4 that were designed specifically for hard disk drives. We are going to talk about some problems that these systems try to address. Then you're going to have network file systems, essentially file systems that are designed to be accessed over the internet, whether on a small scale or a large scale, whether we're talking about something like a Google Drive, when you're sharing hundreds of gigabytes, terabytes of data, or something like your local Plex server that you're using to stream music or videos on your local network. But they are designed to specifically facilitate that access for when I generally say it's the type of file system is optimized for something, I'm talking about the type of storage that it's on. So hard disk drive, SSD, flash storage, magnetic drives, CDs, or and the other element of optimization is the type of data that we are expecting on it. So if we are creating stuff like Plex, for example, file server is designed specifically for media sharing, media sharing on your local network. And taking that into account, it can do some optimizations to basically make it better to use with video data. For example, it can automatically integrate like metadata for videos, for movies, like the name, etc., into the file system itself. That's one of the examples. For example, flash-based file systems or disk-based file systems, we are talking about them. They are created generally for any type of data, but they are aiming at specific media that's used, whether it's hard disk drive or flash-based, a hard data file. And finally, you have distributed file systems like HDFS, SF. These are, if you ever have the need to store a single, let's say a single directory of data across multiple systems. Why would you need this? Well, maybe you need to access it from different points in the world, and it's much faster to, I think most of us here are from Europe, right? But what happens right now is that this stream goes to Microsoft servers somewhere in Europe. I don't know whether they have their. I think there are actually some servers in Serbia. And their servers are actually like in distributing everything to you, but the person, for example, I know that we have at least one participant from United States of America. They aren't accessing this through the server that's in Serbia or Croatia or Greece or Germany or whatever. They're accessing it off of this same stream, this same file. They're accessing everything from the server in somewhere in USA because it's much faster for them. And that latency that I talked about before is much lower if they're doing it that way. So there are a lot of benefits to actually distributing the file system, certain like collection of files or single large file over different servers for various reasons. If this interests you, we are going to talk about that in big data class, elective class. So let's talk about the components of the file system and what most generally what I want to say when I say most, a lot of file systems, different file systems have different applications and everyone can create their own file system. So when I say file system components, not every file system is going to have this. There are a lot of different file systems that exist that they will decide that they don't need Superblock because they are going to encode that data in a different way, etc. So when I talk about this in general, take it with a grain of salt, but most file systems that you will commonly encounter will use these components. So the first thing is Superblock, which essentially contains metadata about the file system. When we generally use the term metadata, right? The data on your computer is what you want, the files that you're accessing, your music, maybe the PDF with lectures, etc. Those are the actual data. The metadata is information that's stored that is basically going to give us information of, let's say, how big is your hard drive, how full is your hard drive, who has the right to access which part of your hard drive, how is that hard drive organized. That's basically the data, metadata, that's going to be stored in the Superblock, and that Superblock is going to be essentially stored at the start of your file system. When I said start, it's easier to imagine it maybe like the starting, the first chip in your SSD or something like that. It's commonly really referred to like the physical start of the storage media that you have. Then we're going to have inodes. Inodes. So basically, most file systems are designed as a network of files that are connected in some way, etc. Each inode will store information about files. So, for example, each file that you have is, as I mentioned, all the way at the start of this lecture today. It's been a while ago, I know. Every file, everything that you have in your computer is stored as a series of ones and zeros, unless you're using something somewhere, exotic file system or storage media. It's stored as a series of ones and zeros. But to actually be able to open it and get a PDF that has text in it, right, you need to know about where this file is physically located, right? Like if you remember before when we talked about hard disk drives, right? I'm going to just scroll back. On this picture of a hard disk drive, this file, right, is stored here, but how am I going to know where I need to move this head and where I need to rotate this spindle to basically start accessing and reading this entire file? Well, this is essentially what the inode tells us. It's going to tell us, hey, this file is located at this coordinate away from the center, and this coordinate, at this level of a hard drive, and it's this long, so we can start reading it and read it in its entirety. Basically, that's what inode tells us. And then we have data blocks that are the actual blocks of data that essentially, contain those ones and zeros that I talked about. Why are we talking about data blocks here? Well, as I said, we have bits, right? And a file might have 32 bytes. That's great. We have 32 bits. If we have 32 bits, great. That's 4 bytes. What happens if we have 33 bits? Are we going to store, 33 bits in the memory, and address it individually? Well, usually not. So for a lot of purposes, it's much simpler for us to, for example, let's say deleting files. If I store something like and say, okay, these 33 bits are this data, and I need to delete it. I need to delete this specific bit by bit, right? If I have a block of data, and let's call that block a byte, like what we used before, and now I'm going to have, I don't need to clean 33 individual bits, right? Which in computer terminology, like we are think of this just as deleting a file, but in reality, this is a series of operation that your CPU goes, okay, go to take this, your SSD, access this specific bit, check this specific bit, delete it. Or if you're talking about hard disk drive, turn it turn the spindle, turn the read head to this specific bit, delete it. Then turn it to this head, delete it. Turn the head here, delete it. Right, set it to 0 or something. If you are a computer science or computer engineering major, I know that this isn't how file deletion is actually done, and you're actually just modifying the inode and leaving the data in place. That's why you can restore the data. But just for the example, I'm using this. So you can delete, bit by bit, or you can tell it like, hey, just delete a block of data, right? Just delete. And if you say, and if this block of data is 1 kilobyte, it's going to delete the whole kilobyte. And that's much, much faster because you only need to give one instruction to delete one element instead of giving 33 instructions to delete each individual bit. Does this waste space? Yes, it does, but usually not by much. And if you want to see like what the bit size is on your machine, on your computer, on if you're using computer or not monitor, create an empty, just go right click, create an empty text document and don't write anything into it. Right click on to it and check its properties, and it's usually going to have a certain size. So for me it has like 2 bytes. Each file has, so that's the block size that essentially stores it. You can, depending on which OS you have, it might show us 0 bytes, then like write anything in it. And so if you like, write information in your document, you will see that the size is going to grow to like 1 kilobyte or something like that. It depends on which system you're using, etc. Basically, this means that basically it grows to like the size of the block because it's much easier to access the data in blocks than it is to access and modify each individual bit of data, right? And the size of this block, how big this block is essentially dictated by, by the architect of whoever created the operating system, and they're trying to balance that. Okay, I don't want to waste too much space, but I also want to not have too small of a block because it's going to create unnecessary operations, right? It's a balancing game. And finally, it's a directory structure, which essentially allows you to have directories. And if you open like your file navigation system, I assume most of you are on Windows, you're going to to decide that tree that you have from your like C drive, going to users, SBS, your username, etc. That's basically the directory structure, and that allows you for organization, right? It allows you to basically compile all of your PDFs that are related to single class into a single directory, etc. This is more of an of feature for you as a user than it is like, for example, data blocks. Most users won't know data blocks exist, won't pay attention to them, but they exist purely, for the computer. While directory structures, on the other hand, exist for you, so you can organize the data more simply. So I mentioned like, file systems basically will give you the ability to do certain operations. As I said, most file systems will give you all of this. For example, some may not enable you file deletion because they are permanent file systems and they are designed to, once you create a file, it stays there forever. This is common in banking, right? Once you create a transaction, you don't want to overwrite it. You don't want to have the ability to overwrite it, right? Because even if you say like, oh, like this doesn't exist, but there's actually like I can access the memory, mess with it, I could delete like a transaction and steal money that way, right? So yeah, some special operating systems might not have these operations. Some might have additional operations such as creating, automatically creating backups, etc. So, but in essentially you will have a file creation which allocates space for a new file. By allocating space, I mean it's going to be like when you create a file, like I said before, you create an empty text document, is going to reserve a single block for it, right? And depending on the size of the file and like your program, you can actually allocate much more space to it. You can allocate a couple of megabytes if you expect it to be, you know, a large file, etc. And this makes sure that while you're working on a file, you have enough space to create it. If in previous classes, if you used Python to create a file for something, I don't know if you did it, but when you have like a file open, right, if you used open, it essentially does this. It creates a space that you can write to and store it. In some, you know, more strictly typed programming languages like C, you would actually need to tell, hey, allocate this much space for me in this operation so I can write to this file. Again, file deletion, you know, free space and removes the file entry. As I mentioned just a bit before, what file deletion usually does is it deletes the inode, not the full. So if you have a text document and it stores some data, it stores some text in the memory, when you click delete, it just says like, hey, this file doesn't exist from the inode perspective. That data is still written to the hard drive, and it still exists there, you know, but you can't access. There's no way for you to simply access it because you deleted essentially a pointer to it. If you are coded in C or C++ or similar language, you use pointers, memory pointers. This is essentially you're deleting a pointer and you're still leaving the data in memory. What this means is basically your file system won't let you create a file that points to the same bit of memory. So it will automatically, you know, check if memory is free or not through existence of inodes. So basically, this allows you to, like, when you delete the file, you know, it's that memory is now free real estate because there's no inode pointing to this thing. Like starting here, going forward 50 blocks of memory, it's a file, a singular file that you can't write to. So in that case, if you accidentally delete something that you shouldn't, like permanently delete it, like shift delete it, not just move it to a recycle bin, the first thing that you should do is like shut down your computer, like unplug it from you know, your electricity supply, and put like a Linux that doesn't, and try to rescue that file. There are specific tools that allow you for file rescue, right? Because that data still exists in memory. It just doesn't exist from like the abstract point of view for you as a user. Some file systems, on the other hand, that are designed to be more secure or something, do actually, you know, try to wipe that memory by setting it all to 0. That's also not a guarantee. Like if you're selling your computer or something. When I was a college student, I actually had like a side gig refurbishing computers, and I would buy like old computers, fix them up, and sell them to other students and stuff. A lot of people would like delete their files and like just booting Linux and entering in it without actually reading files. You can see that the files are still there. You could access if you wanted to. I obviously never did because that would be wrong, but you could access someone's files. So usually my general advice when I give it to people is like, if you're selling a device, buy a different hard disk drive, put it in and before you sell it, if you can afford it, or just use their tools out there that are created to completely wipe your with some advanced techniques. Because even just writing all zeros, let's say your magnetic hard disk drive, won't necessarily completely remove your files, because for the nature, like for example, I mentioned before, you know, a zero can be everything from 0 to 2 volts. So if you're having like, you know, in your flash storage, you have like 2 volts stored there, and you delete it, you write 0 to it, it might not bring it to 0. It might bring it from 3 volts to 2 volts. And using that, there are algorithms and softwares and techniques that actually allow you to recreate files after the deletion. There's a funny anecdote from a friend of mine who worked in the military. I was curious and I asked them how do they like delete their files at the military level, and he told me they use Sledgehammer. And I asked him like, I'm not familiar with that software. He told me no, we actually use a Sledgehammer. We just take our drives out, put them on the ground, and hit them with a Sledgehammer to completely destroy them, because we don't trust them. There are actual devices out there that are designed with the pure purpose of destroying hard disk drives and SSDs, completely shredding them so you can't get information out of them. It's a whole field into its own, like forensics on the hard drives and SSDs and any other types of storage. So just it's a bit of an aside, but be careful when like deleting files are it's actually like much more complex topic than what most people think it is. Same goes like with file access. When reading and writing data to files, basically means like, can I modify that part of memory? Can I see what's in that part of memory? And finally, like modification is similar to writing. You're just updating it without actually changing anything. So if you're creating a new file, or writing something and you're creating a new inode, if you're modifying the data blocks within an existing inode. That's the difference between that. Okay, so as some of you know, you have file extensions that are used to identify the type of a file. For example, .txt is a text file, .jpeg or JPEG or PNG or whatever it is. An image, ISO is a system image, etc. Not all file. This is basically a hint, right? Some operations like Windows use this by default, but you can. This I actually don't know if this works. If you create a new text document. And I think by default, most Windows systems today actually don't show you the extensions. You can look up online how to turn on the extensions, and then you can actually delete the extension. And once you hit enter, it's going to tell you if you change the file name extension, this file might become unusable. If I click yes, you're actually going to see, if you do that, that the icon changes. And once I click on this, which now instead of being named new.txt is just named new, when I double click on it, is going to ask me what app can I use to open. And if I select Notepad or Visual Studio Code or any text editor, once it opens it, it actually has the same, for me at least, this can probably vary system to system, it has the same information that was actually stored, so I can still store text in it, or I can write text to it, save it, exit it, but every time I'm open it, it's going to ask me like, hey, what kind of software do I need to use to open this? And it's right, because it doesn't have that extension, it does have that txt that tells it, hey, this is a text file, use Notepad to open me. That's how this file is shaped. That's the type of data this file contains, right? Okay, so that's essentially what extension is, and some file systems don't use them at all. Some use them, just as hints, as I mentioned. Some require them. It varies. Just a hint. Usually, this was a relatively funny situation. I was actually recently contacted by an old colleague of mine. He told me like, "Hey, I have these files that are specific to this really expensive software for this thermal camera that we use. I'm not going to name which camera it is." But they essentially they don't support it anymore, and we can't get the software. So the camera is completely dead, and we can't use like it works, but we can't actually open the pictures taken from it, and the company essentially told us like, hey, this is abandonware, we don't care about it, it's old, if you want support, if you want software, buy a new one. And he told me like, can you try doing something with it? So he sent me the files, and he told me like, try to write some code that is going to enable us to open this file. And I opened the file with Python, like I loaded it into the memory, and I saw it was essentially just a picture, like it was just a bitmap array, like any picture that you would like, a PNG or a JPEG or anything. The only difference was that they essentially changed the file extension to something like, I would name what it was, but so instead of PNG, they named it SBS, for example. Those are just my initials, and the Windows didn't know like, how can I open this file? It's not an image, or at least like the system they use. I don't know what would happen on like a more modern system. So yeah, sometimes manufacturers will lock things down using just using standard system with just a different extension. So that's a little hint for you. You know, if you ever run into a situation like that, if you expect an image, try to just, or a text file or anything, just try changing the extension and see if you can open it. Okay, yeah, what I had more to mention, basically when it comes to file names, some file systems have a reserved link for it, and some are case sensitive, some aren't. Some file systems don't allow certain type of files. So, for example, in Windows, if you try using, I think you can't use question mark, right? It's going to tell you like, hey, you can't use any of the following characters, and at least like 10 characters that you can't use in file names if you try naming them. Uh, some files is like a famous example of this is like, for example, I usually prefer using Linux, and I usually prefer navigating stuff with terminal. So I always hate it when there are like spaces in file names, because it creates some issues, because initially it was designed the Linux terminal and some tools in it were designed assuming that you can't have a space in the file name. You can these days, so yeah, it can sometimes create issues. Okay, I mentioned like security again. Security is a wide term, and this isn't something. When I say, when I'm talking about security at the file system level, that's not real security. I wouldn't enter into that topic. It's, again, we could have a whole course based on just. We're actually talking about having a project that just focuses on educating people in cybersecurity. It's a whole area. So when you're talking about permissions, this is like a base level security, and there are three types of permissions that you are going to have in most file systems. That's read, write, and execute. Read will allow you to open a file but not to change it. Write will allow you to change the file, and execute is, a special permission that tells you essentially like, hey, this is a program, you can run it, right? So this will control, basically, can you run a program or not, and can you execute something or not. So, for example, on Linux, depending on how your system is configured, if you have like the execute turned on for your Python, once you double click it, it's going to run the code that you've written in that Python file. If you don't have the execute flag written, you're going to open it as a text file, as a code you can edit. So that's an example of this permission. Basically, if you look at chat, I'm going to write something like how it basically looks. You will have something like this. So you will have a dash. That dash can either be a D or a dash. In the start, I didn't put this on slides, I apologize. But essentially it says this is a directory, or this is, if it's a dash, it's a file. And then you have this RVX, R, R, W, and X for read, write, and execute. And it says for like anyone connected, people in a certain group this file belongs to, because you can create groups of users on Linux, and the specific user this file belongs to, and you can control access. So, for example, if we say something like, if you write, if you use Linux, or if you're using Linux, when you're listing files, use LL instead of LS, and you're going to see this. If you see something as I wrote here, so you have a dash, that means it's a file. Then you have r dash dash, that means that all users that aren't, this file doesn't belong to, can read it, right? But they can't write to it, and they can't execute it. Any people that are in the same group as the user who created the file, who is the owner of the file, can read it and write it, right? But and all the users, like the actual user, can read, write, and execute. So using that, just to give you an example, for example, here you are participants, you're everyone here. Then we have me, who is one of the organizers of this, and we have lecturers, right? So for example, I'm in the group of lecturers. So for example, for the PDFs, right, that we are sharing, slides and everything, I can do whatever I want to them, but I can delete them and everything, because I have created the file system where they are shared. Every lecturer can upload and check other people's slides, and upload their own slides, etc. And you, as general participants, you can only read those slides, so you can't upload your slides, or you can't execute by execute, I mean, any other operations, so like a delete or whatever, with those slides, right? So that's what file says, like permissions vary based on file system and operating system. So for example, execute doesn't make sense for a lot of file systems, like for example Google Drive, because I already used it, doesn't allow you to have executables, and even if you have an executable uploaded there, you can't run it. So there are different operations like deleting and certain types of modifications that some users can, some users can't do, instead of execution, right? Okay, so the what we are going to cover now are some common file systems that we have here, that you will find. Why is this important? This is important just in case you ever need to create a file system or anything up. Sorry, you ever need to like create a file system? Maybe you're formatting a drive or something. So let's see like basically what file systems exist. NTFS is basically the default if you're creating a drive for a Windows environment. Windows is creating a drive for you. Usually you are going to be using NTFS. ext4 is what's used in Linux systems. FAT32, right, is very popular system. You can see that, like, I automatically went to say it in Croatian, like FAT32, because it's very common. It was the default system usually used. 32 is there because it used 32 byte-sized blocks. And basically, it was extremely simple because at the start of that, what I mentioned, like that super block at the start, basically told you all the information and for all the files on there. And it told like, okay, so from this block to this block, you have this file. From this block to this block, you have this file. And it was very simple to use. It was very simple to write, and it was great for big files. Because if you had a ton of small files, it was very, very slow, because the super block got really, really big because it needed to list every file individually, right? And yeah, and it wasn't really great. Block size was relatively big, right? And people didn't really like using it. But essentially, if you have any device and you aren't getting it to recognize your USB drive. For example, you have like an old printer and you want to like update firmware on it, or you want to like print off USB and it's not recognizing the drive. Format it to open my computer, right click on the drive, make sure all the data is backed up, because formatting will delete the drive. right click on it, format it to FAT32, and it's going to read it. That's like is the simple system, and usually it's what's causing what's causing the problem where your USB can be read by some older device. And then we have exFAT, which is just extended FAT. I forgot to mention FAT means file allocation table. That's that super block at the start, which basically says like this file like that's named like this is from this block to this block, right? It's just like a table that's compared to like some more complex like net grids and network-based inode structures used in more advanced file systems. exFAT is just extended file allocation table that's optimized for larger file sizes. Actually, the FAT32 had like an upper limit of 4 gigabytes or something like that for file size, which back in the day was like, I don't know what you could store that was that big, and it would probably take hours to copy and paste anyways. But today, if you have the video of this lecture is probably going to be over 4 gigabytes in size, right? So it's not really great. So but as I said, a lot of older hardware expects FAT32. So exFAT is an attempt to make it backwards compatible with FAT32 based devices. It tends to work, but again, it's not great. So you can try using exFAT if you need to, compatibility with an older device. But it's not a guarantee that it's going to work. So it's better to just use FAT32 unless you actually need like more than 4 gigabytes or whatever the exact limit is. I know it's around 4 gigabytes. In addition to this, you have journaling file systems that are specific types of file systems. Why? Because, well, some operations take time. If you are copying or pasting something, right, it's going to take 10, 5 minutes, 40 minutes, depending on what you're doing, how you're doing it. These file systems like X4, NTFS, and some others essentially tell you like, okay, at this time, we have started the operation of copying this file from this destination to this destination, right? Bam, electricity disappears. You try to reboot, and it's going to say like, okay, we have a journal. What happened before there was an interruption? Before, the computer lost power or something. Or we were copying this file from this file. Obviously, that file hasn't been copied because we didn't write that this copy has been completed. So we're going to delete it, right? We're going to just nuke it. And we're going to maybe in some cases restart this, or we're going to let our user know like, hey, this wasn't copied, right? Because the last thing you want is, for example, if you're copying a file, let's say you're copying something like a video that is going to like be, 2 gigabytes or something. You're copying it and you lose connection, like your USB, like you hit your USB, you lose connection for a moment, and you think, and it stops the copying, and you have like a part of the file there. This you can sometimes experience this with like files downloaded off of the internet, even today. You don't want that because you think that your file has copied, and even worse, because the size, like when you're copying the file, what happens first in your file system, file sizes, data blocks are allocated and written to the inode. So if I'm copying a 4 gigabyte video to my USB, first thing that's going to happen, even though it didn't actually write the data, it's going to say like, oh, this is a file called somevideo.mp4, and it has 4 gigabytes of size, despite the fact that I haven't actually copied a byte yet. Why does that happen? Because the file system has reserved space for that file. And it says like, oh, these 4 gigabytes here are reserved for this file, and it's going to show us that file having 4 gigabytes, despite that those data blocks are still empty or they have some old data on them. And what happens if like my USB loses connection? Well, I'm going to check it and say like, oh, there is a 4 gigabyte video file here. I think that works, and I'm going to bring it to a different computer, turn it on, and it's going to be corrupted, right? Because maybe part of it will work, but not completely, because some data copied, some didn't. It's going to be very, very, it's going to be problematic. It won't show the video, but I'm going to think it has been copied. So journaling file systems try to address these types of errors, right? By saying like, I have started the copy at this time, and if there is any issue, they will check that log and say like, oh, there should be a corresponding entry here, saying that if I have started the copy, there should be an entry that says that I finished copying. The reason that means that this file hasn't been written properly, so I'm just going to remove it from the file system and notify my user saying like, hey, there was an error, right? And that's why essentially when you are, that's essentially what prevents you from errors in these types of file systems. And it allows you to be like, hey, this is what happened. This is an error. I can just copy it again. Some more advanced file systems are actually, as I said, some file systems expect like, okay, you're just going to post videos to these file systems. Great. We're going to like write sequentially, and instead of if we're copying something, we're actually going to track frame by frame what we copied, what didn't. So if there's an interruption, we can continue the copy process here, so it doesn't break or something. That those are like more advanced, more specialized file systems that I mentioned before, like Plex, etc. For this type of problem, or like Samba, that is a network file system that interrupts. Like, hey, there could be an interruption to my Wi-Fi or something. So I'm going to be, I'm also going to use journaling, but I'm going to enable like longer waiting, and I'm going to store more information there and use that information more smartly to see if I can manipulate this file system in case there is an error, dropped connection or something. So I can actually restart downloading. Some of you may remember that back in the day, if you started downloading a file that was very large, like you're downloading, I don't know, and Ubuntu ISO, most people preferred using like for Linux ISO, they preferred using torrents, not only because they were faster, but because they were actually allowed, if there was an interruption, if your network died or something, you could actually continue downloading a torrent back in the day. And if you have any like older system engineers or system administrators that you can talk to, they will probably remember that at some point they have argued with people in their administration about how torrents should be allowed on their network because they're trying to download Linux ISOs over them. Especially on older, slower networks, right? If you're downloading in a standard way, just download, usually using FTP or protocol like that. We're going to talk about protocols in the next lecture, I think. If you're downloading something over FTP, it's just going to break. If you lose connection, if you downloaded 1 gigabyte out of 1.1 gigabytes, and your connection dies, you just lose all the data, and you just need to reset. That's how it was back in the day. Today, most browsers use protocols that allow you to essentially use journaling, and they know how much data they have downloaded, and they will be able to restart the download, right? Like you could do back in the day with torrents. I'm not going to enter about like why you could do it with torrents, why you couldn't do it with files, and why you can today. But essentially, a journaling that allows you to know which part of a file exists on your file system and which doesn't, are a big part of why that is possible. Okay. So I mentioned that file system performance is influenced. That file system performance is influenced by block size and this is called access patterns. Basically, if you imagine your SSD as a grid with information stored on it, if you have sequential reads, right? That's one of the big examples why SSDs are much faster. If I have a piece of information here, right? and then I need to access a second bit of information, and that bit of information won't necessarily be stored here, right? There are a lot of reasons why, but what you need to know right now is that it won't necessarily be stored here. It may be stored here, 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 at any random part, at any random chip. That's not a problem because with an SSD, I'm directly accessing it. I'm accessing this and this, then this. It's same if I tell it access address 14 and then access address 15 and then address access 16 to an SSD. That's the same. That's pretty much the same as me saying, okay, access 1476, 129, 2, right? If I'm jumping around. With SSDs like this, that's not the case, right? SSD wants all the information right one after it, because that makes it much faster to read the data, because it doesn't have to move the arm, it doesn't have to spin this, because if you have a piece of information here where this file starts, and the SSD rotates clockwise, and the next piece of information is just one bit to the side, counterclockwise, you need to spin the whole drive, the whole circle to get to that information. That slightly slows down an HDD, but if you're constantly doing that, there's a significant penalty to reading the data that way. Older types of drives, like the RAM drives that I didn't mention here, suffered from this horrifically. But for example, here in modern drives, that's not a big problem. And that problem of like this data is written here, then here, then here, there are a lot of reasons. For example, if you're trying to write 4 GB long video, that's going to be 200 data blocks. Those 200 data blocks, you might not have space on your hard drive to have 200 data blocks one after the other. So you're going to write 50 data blocks here, 50 data blocks here, 100 data blocks there, right, in different locations. And this can reduce performance. So in old computers, you used to do defragmentation once in a while to basically move files around and put them together, right? Today, this isn't necessarily the case. Is not that big of a deal with SSDs. There are still some benefits to having your files not fragmented, right, and having them in individual, places, like one after the other, because it simplifies certain accesses and stuff like that. As it says here, like file system optimization can reduce overhead. If I don't need to think about where the next file is, but if I know that the next file, if my file starts at memory location 14 and I know that my file, the entirety of it is in the following 6 blocks, so memory location 14, 15 up to 20, I don't need to communicate with my super block, my file allocation table, whatever it is, to tell me where the data is stored, and that lowers the overhead, that lowers like the lookup. So because I can go like, okay, read 14, am I up to 20? No, read next. 15, am I up to 20? No, read next. So I can just like use essentially for loop to read everything instead of going like, okay, 14, let me go back to my super block, let me see where the next is. Oh, next is at 120, let me check it. So while it is much faster with an SSD than it is with a hard drive, there's still penalty to fragmentation. Another thing is that helps this is caching. Caching, like I mentioned it before, that you can use like a faster drive and copy files that you want. This is a similar thing because, for example, I can have, if I'm reading, for example, if I'm looking at a video and 1 second of a video is, let's say 30 seconds of video are stored from memory location 1 to 100, and then next 30 seconds of a video are stored from location 200 to 400. But computers can read this information, these seconds of video, much faster than the actual video is playing. My computer, right, can automatically load the first 30 seconds of the video into RAM, let them play for me, and while I'm watching these 30 seconds of video, which it will let it copy it to RAM in under a second, it can cache, it can preload the following information, right, following 30 seconds from any location to RAM for me to read. And this is essentially buffering. If you have like a buffering problem when you open like YouTube, back in the day, you could see like I don't know if you can see it on newer YouTube updates. You can see like a secondary bar, like going ahead of where you're actually watching. This is that buffering, creating like caching, copying like the video that you're about to watch in advance, right? And in good old days back, before optimization, everything, you had the slow connection, you could let the entire video download and then watch it, but we don't do that anymore because it causes some unnecessary loads on the server, because not everyone watches the entire video, and etc. It doesn't matter here. And this is basically what I mentioned, when it comes to file allocation. Contiguous or continuous allocation is, files stored continuously in a block of memory. So every block, right, is going to be, you're going to have like, if this file is, I don't know, 100 bytes, that's going to be 100 blocks on our system. It's going to be 100 blocks, one after the other. This is the ideal, but it's not necessarily the best. Then we have linked allocation, where files, where you have like a few blocks, and then the last block says like, hey, this file is then in, so we have like first 30 seconds on the video, and the last information that the computer will read from the short is going to be like, hey, the next 30 seconds of the video are at this location. Then you watch that 30 seconds of video, say, hey, next 14 seconds of the video are at this location, right? And the computer will automatically take care of loading this. The third is index allocation, where you have like a table of indices. It says like, instead of that information, like where the next part of the video is, you're going to essentially have a table that says like, hey, the first 30 seconds of the video are from this block to this block, and then the following 30 seconds are from this block to this block, and so on. You won't see any difference, except these two might be slower, right? Having a contiguous allocation. In the end, as it says here, each method has advantages and disadvantages. Contiguous allocation might seem perfect, it's all in one place, but the reality is, you can't guarantee it, because if you don't have space, you simply need to break up a file. Or maybe, as I said, hey, the documents that are, physically closer to something, if you're storing something that's important, quickly accessed, like, hey, I would prefer at least a part of it stored in my cache, very close to my RAM, so I can, very close to my CPU, so I can process it quickly. I know, like, the rest is going to be stored at a more distant part of the memory, but that's what can I do? Yeah, so there are a lot of benefits, where that in most cases, like in most cases, you want continuous allocation, but there are some special cases where splitting that file simply has to be done or is beneficial, because you want to take ability, like, the best example I can give you is, I'm processing pieces of data, and I want them, in my cache that is 64 megabytes. So I'm going to split all of my files into blocks of 64 megabytes, and I'm just going to load them into the cache one after the other, and I don't have to worry about, if I'm using a linked allocation, I don't have to worry about or index allocation. I can keep the index of where the next file is. Next part of the file is in my level 1 cache, which is like very small but very fast, and I can keep the actual data, in L3 cache, and virtually, to me, it's going to look like it's very fast. And because it has been split up ahead into different parts, I don't have to worry about splitting it using overhead and adding overhead to the method, because it's already split. It's already had pointers added to it, or the index, table was created for it. Yeah, that's essentially, what I can essentially use this. What I'm trying to say is essentially, some of these methods have benefits, even though they aren't readily apparent to you. And again, this is, I already talked about fragmentation and the fragmentation. It was really really fun. to do the fragmentation back in the day because it had a nice animation of like but nice animation for Windows 95 and Windows XP days, not what passes for nice animation these days. Where you could see like the individual blocks moving and they were colored in different ways, etc. So a lot of young computer nerds, maybe including me, have worn their disks down by doing the fragmentation way too often than it was necessary because we knew that it improved our performance, so we did it all the time. Damage to our drives, non-withstanding. Uh, yeah. Again, these days, this isn't that big of a deal because journaling helps us track not only like for error prevention as I mentioned it, but helps track where everything is written to. Back in the day, like for example, if you're using file allocation table, table here is key in that FAT32 system. You need to create a new row for each fragmentation of your data. If you're using a journaling system that uses a journal instead of allocation table, you don't have to worry about that, right? Because you can just use pointers and because you're already splitting into blocks, you're probably just adding like an additional block of data. You aren't adding a ton of new data thanks to that pointers and whatever. So fragmentation isn't really a big problem today. And in case where it is, you don't have to worry. You don't have the fragmentation tools for your SSDs or whatever. You will probably have a defragmentation tool on your PC. But if you open it, right, I have just opened you can just hit start, type in defrag, and you're going to see that it basically says solid state drive, and it's going to say something like it's going to have status, and for me it says like, okay, 2 days since last retrim was performed. That retrim is something that that basically checking the health, as I mentioned, of SSDs, anything that is performed automatically by the SSD and by the drive. Like if you have a hard disk drive like I do, it's going to actually tell you how fragmented it is. For me, it's 0% fragmented because I don't really use my hard disk drive. It's very empty, and you will see that you can't even, if you have an SSD, it won't even give you an option to analyze it or defragment it because, well, you don't need to do it for an SSD. Okay, so let me see. Okay, I have a few more slides. Let's talk about virtual file systems. So, as I said, file systems allow you to address certain data in a certain way. Sometimes for certain applications, you want a different file system. You want that application maybe general. Maybe it's not something that you want to use for everything. Again, maybe you're doing a lot of manipulation of a certain type of a file. So you want a specific file system that works for that works better there, or you want certain features that your file system doesn't offer you, but you want them in a specific example, or maybe you're interacting with a server somewhere that uses a certain type of file system, and you want to facilitate the usage between your two file systems, right? So in that case, you can create a virtual file system that essentially creates a middleware file system for you, and some types of applications will create this. If you have any creation that has its own files, that access its own files in some way, some video editors do this, some specific scientific software does this. It creates it. For example, my field of study is robotics, and the simulation software that I use is called Robot Studio, and it basically enables you robot has essentially each industrial robot that you're going to use in the world today has its own computer, right? And that computer, control unit, it's called. It's not just a computer. You can basically, if you're simulating something, you can actually simulate the file system of that computer. So, for example, if I'm running a simulation and I want to read and write certain files or programs for the file system to my robot, to my virtual robot in a simulation, I will actually have a virtual file system created to me by that software, a Robot Studio, that I can drop files to, right? And it's going to act like it's the actual computer that's controlling my robot. And then I can actually take that data, that file system, and just directly throw it onto the control unit or the actual robot that I have in the laboratory, and it can use, it can read and write the files in the exact same way that programmatically that file usually does. What does this mean to me? It means that, for example, if I'm doing a measurement, for example, for my PhD, I'm measuring the energy the robot uses. If I'm doing that on my real robot, I don't have to figure it out, down there in the laboratory, try to figure out like how does this work and everything. I can use the program. I'm using the programming language is called Rapid for the Robot Studio, APP robots. I can figure out everything, how to manipulate the files in the simulation, and then just use the code that I've written on the actual robot in the laboratory, because it uses the exact same file system. Okay, so that's the example of virtual file systems that you may use. I mentioned before distributed file systems where you want to store data across multiple machines, not necessarily the same data. It can be like the same data on different computers, right? Or it can be parts of data on different computers, etc. There are a lot of different approaches to this. What's important is that it's going to support redundancy, fault tolerance, in sense of like what the data is where. What if system 1 has a newer version of than system 2, or worse, a different version, right? What if I access the file and I know the colleague here, Leo, accesses the same file and we both change it at the same time, but he changed it on one system and changed it on a different system. What happens? Which file is the master copy, so to speak? These are some issues that happen with distributed file systems. Again, we're going to discuss this deeper in big data, right? The most famous example is Hadoop distributed file system, HDFS. That's usually what most people, when they talk about distributed file systems, base their discussions on. And basically, these file systems are just special file systems that are designed to keep track and journal across different machines. Machines that are possibly very distant and that have a lot of latency in their communication. Right. And they're often used, as I mentioned, in cloud storage, big data applications, right? As I mentioned, if I upload a file here to Google Drive, all of you aren't probably accessing the actual file physically, that I uploaded, because the drive that I uploaded to the server that Google uses is maybe in Zagreb in Croatia or Belgrade in Serbia, or Italy, Milano. I think that there are servers there. But depending on where you are from, you are probably accessing a completely different server, and but you're accessing the same data because Google, in this example, uses a distributed file system that assures that when you try to access this file, that when I send you the link to the drive, as I said before, you are accessing this file at the server that's closer to you because it's simple to them, and everything they're trying to make sure that that file is the same copy that I sent, that I uploaded, same version that I uploaded, etc. Like that's what distributed file systems exist for. Another special example is network file systems, which allow you sharing file over the network. Some of you may have considered setting something like this up for, you maybe wanted to have like a central network attached storage that allows you to access data and from different computers, like for example, I have a central computer for different types of media, so me and my girlfriend can both we have one copy of the video, like movies, and if she wants to watch one movie on her tablet, I want to watch a different movie on my computer, we can access it on the same server, right? This is called a network attached storage, and basically there are two systems that facilitate this. You have NFS, Network File System, and SMB, Server Message Block. A more popular implementation, just so you don't confuse it because it's essentially ubiquitous, is Samba, like the Samba dance. That's basically an integration of Server Message Block that's used for accessing files in Windows networks. So if you ever hear of someone talking to you Samba, they are using SMB. Yeah. And it provides remote access to files. Essentially, if you open my computer, in addition to like your local drives that you have, you're going to have an external drive that you can use to share files. Yeah. And from your perspective, it's the same as if you have a hard drive that you're copying data on or off, but that is accessible to everyone that's connected to your network, which can be a good or bad thing depending on how secure your network is. But again, I want to enter into that. And talking about not entering into that, we have a file system security. As mentioned, again, security is a wide area, but file system security aims to ensure confidentiality. So confidentiality means that the data that you have that you want to keep confidential isn't seen by anyone you don't want to see, right? Integrity means that the data is the same as it should be, right? So let's take, for example, if here your ID, right? You don't want anyone to have access to your ID because they could open a bank account or something with it. So you want it confidential. You also wanted to have integrity of it, right? So you don't want me to be able to take the picture of your ID, right? And modify like your birth date and upload it and get you arrested because you used the fake ID. Or just, you basically want it resistant to modification where it's not appropriate, right? And availability simply means that it's available to you. You can access it whenever you need it. You don't want, you don't want that data to be not available when you need it, right? Because there was an error or something. These are different types of security attacks. Again, this is something that we do discuss in big data and file system. No, yeah, we don't enter it here into different types of security threats, but there are attacks on confidentiality, integrity, and data availability. Usually, the simplest thing that you can do is access control lists who define who can access files and not. So for example, like on my home network, if you come to my house, you can use, if I give you the password, if you scan the QR code that I have, you can connect to the internet. So when my friends come to visit, they can connect to the internet and use everything, we'll go online, chat, but they can't access my file server that I talked about before because I encoded that. So it has an access control list that only, my laptop, my girlfriend's computer, my computer, my phone, and I have a list of certain devices that can, using the MAC address, can access it or not, right? Isn't perfectly safe, but it's safe enough that, I trust my friends that they wouldn't like damage my data on purpose, but I also don't want them to accidentally upload or download something they shouldn't. So that's the simplest possible way. Another way that you can do it is encryption. Basically, encryption means that you are using, there's difference between encoding and encryption. Basically, encoding just transfers the data from something that's readable to something that's not readable. Encryption is encoding in a way that you need to use some secret information to get it back. So, for example, when we talk about converting value of 3 using IEEE 754, that's encoding, right? Because you know, if you know the way to get it from a value of 3 in decade, you know how to encode it in binary or IEEE 754, and you can get it back, right? But with encryption, you don't, right? Encryption, you need to have some secret information, whether it's algorithm, whether it's a password, whether it's something that protects your files from unauthorized access. And it's very important advice that I always share with people. You can encrypt your hard drive, do it, because today you don't want to lose your laptop and have it completely open. Not just, because having password protection so I can't log in means absolutely nothing. Because, for example, if you're using an unencrypted file system on Linux or on Windows, it doesn't matter. Your password doesn't mean anything to me because I'll just plug in USB, right? And I have direct access to your file system without needing to type in your password unless you have encrypted the file system. I'll admit I'm not sure how to do it on Windows, but if on Linux, when you're installing your OS, you can just choose to have it done automatically for you, right? And that makes sure that I can't, or that someone who steals your laptop or your computer or whatever can't access your information. Yeah, without also knowing your password. And just pointing out again, there's difference between password protection, because if you just have a password set up on your machine, if the person who has access to it has any knowledge about computers, it means nothing, right? It's not even a problem to get around it. Like, it's not even worth mentioning. Uh, okay, and finally, auditing. Auditing is basically, if you're journaling, you can where that tracks, files. You can audit that. You can take the journal of changes and you can check it, and you can say like, was there any like copying, or is there any operations that I didn't see? One of the examples for this is today very, very popular. For example, if there are any creations here, you know that a couple of months ago we had a big problem in one of the largest hospitals in Croatia. Had a problem with ransomware, where ransomware, basically what it does, it locks down your system, and you need to pay a lot of money to someone to get access to it. And they will probably, if you pay them, they will probably give you the password that you can type in and unlock your system. For example, because that's a big problem today, and a lot of companies. I mentioned this Croatian hospital in Zagreb, but Boeing was a victim of it a few years ago. Um, you can essentially, your files are held ransom, and what there are softwares, anti-ransomware softwares, because encrypting a file is sometimes slow, especially if you want really hard encryption, as ransomware does, because you don't want someone to be able to crack it. We'll use journal auditing to figure out that ransomware is encrypting your files and is going to basically shut down that process. Is going to like forbid that software for accessing the files. Is going to notify you like, hey, I'm noticing there is a software encrypting something. I've noticed that there is a journal. In the journal, this it's written that the software has essentially tried encoding something, tried encrypting something. Is this something that you're doing, or are you aware of this? I'm simplifying the things a bit, but That's essentially how you can detect, and prevent ransomware from happening through, checking what's going on your file system. Another, problem is consistency. I mentioned that before, in distributed file systems, but it can cause issues, on the level of a single computer. What we have two. I have, the same presentation open at the same time in two instances of PowerPoint. And I click save at the same moment. What if I'm editing a file and it crashes? My computer dies. As I said, journaling is one example. Another example is checksums, where you can basically take all of those. I'm going to simplify checksumming a bit. It's not exactly how it works, but just explaining the spirit behind it. You can, again, this is introductory class. If you're interested in algorithms for generating checksums, you can check them online and see how they exactly work. But to keep it simple for everyone, you can do like if you have a big file, you can say like, okay, I'm going to go block by block, and in each block I'm going to sum how many ones. I'm representing this binary. This file is represented binary in my file system, so I'm going to check how many ones are in each data block. So we have something like 5 data blocks, and I'm going to be like, okay, so in the first data block I have 5 ones, in second I have 7, 3, 2, 5. My checksum is going to be 7, 5, 3, 2, 5, or whatever I said. And I can, when I'm sure, like I just created the file, I'm going to create that checksum and write it next to the file. So I know that this text file that they connected has a checksum, I don't know, 723. And later on, if I'm unsure of its I'm unsure if it's fine, if it's consistent, if there wasn't an error, if it wasn't modified in some unwanted way. I can check the checksum again, and if that original checksum was 723, if I run the checksum again and it returns as a different value, it means the file was modified, right? Of course, this simple algorithm that they described doesn't guarantee a unique checksum for different files. You can have a file modified in a way that gets the same checksum with this algorithm that I described. It's just a very simple example to illustrate it. Why there are better algorithms for generating checksums that you can check online. But why is this very interesting? Because summing is one of the basic operations on computers, and it's very fast. Because every mathematical operation can be defined as a sum. So subtraction is a summation with a negative number, so the complement of the number. Same goes for multiplication, is just a summation repeated. You can define division with summation as well, pretty simply. So because of that, most computer operations are based on summation, and it's very, very fast. And that's why it's optimized at the hardware level to be very fast. And that's why creating a checksum is very fast, and we can easily validate a file using a checksum, right? So that's something that's commonly used, and a lot of files that you download back in the day, it was much more common, but for larger files, to have them delivered with a checksum that you could easily check to make sure that when you downloaded the file, it was fully valid. Okay, so what is the process? This is something that I just wanted to mention. Basically, it's file system mounting. It's something that you're going to see a term that you will be able to hear, oftentimes, if you're dealing with computers with file systems. Mounting simply means that a file system is connected to your directory structure. So, for example, let's say you have a hard disk on your computer, and if you're using C, it's usually going to be if you're using Windows, it's usually going to be marked with letter C. if this is one of my classes, I would usually, give a bonus points to people who find out why isn't it A or B. A was reserved for floppy drives, B was reserved for a different type of storage. I think it was not CDs, it was something else. But A and B were reserved for different types of storage. So C is the default for drives now on Windows. And I wanted to add a different drive. And what your Windows does automatically is going to create another letter drive that's D, right? Or E, F, G, whatever you're creating. And these are basically two separate file systems. We have a base file system of your Windows that's abstracted above it, and then you have C, and then you can add an additional file system on your new hard drive or whatever you connected to it as letter D. Then you connect a USB and you can connect and that's a letter E, and it has another device and another file system, because each of these can have different file systems. One can be NTFS, one can be ext4, one can be FAT32 or exFAT, and mounting basically allows you to access these file systems, right, separately, and in addition to accessing these file systems separately, is going to make sure they work nicely together. So if I'm copying something from my D drive that's exFAT to my C drive that's NTFS, is going to take care of converting and everything for me. So it not only allows access, it allows integration of multiple file systems on a single machine, right? And it enables creation of a sub file system, so I can split virtually my external disk into two, and despite the fact that it's a single media, right, it's a single hard drive, I can have a D and E file systems on it, and and I can have a D mounted as NTFS and E mounted as ext4 because I'm running some Linux off of it or something. Yeah. So that's what file system mounting essentially allows us. And finally, yes, not for safety and security, not all, as I said, Windows does it automatically. As you plug in your drive, you plug in your USB, it's going to make that ding sound and you will have access to it. Back in the day, it used to ask you what to do with this drive. It might still sometimes do that. I'm not sure. Windows has weird ways of working, but yeah, it didn't automatically. It usually automatically mounts it, but not always. I think if you plug in a new drive, it's going to ask you what are to do with it. On Linux, it depends. Some modern Linuxes will also assume that you want it mounted if you plugged it in. And then give it access to your file, which is unsafe. Again, a little tidbit on computer security: if you find USB, never plug it in, right? If you find the USB on the floor, only plug it into computers you don't care about, because there are a lot of types of attacks that can either damage your computer using something like USB killer, if you want to look that up, or just execute something that's called a rubber ducky that basically executes commands and breaks your system or uploads it somewhere or something. But basically, even without that, right, you don't necessarily want file system to be mounted automatically when you plug in your drive, because it can cause some issues, even without like those extreme, let's call them examples, of security breaches. And so while some Linuxes will assume today that you want it, a lot of older systems will give you access, but you will need to manually go into the terminal and mount the file. So essentially attach the file system that exists on that drive to your drive, and you're going to need to specify which file systems they are in some cases. Yeah. It basically allows, as I mentioned, integration between file systems, and for security, it's not advised to be able to do it automatically. Okay, so let's just mention another few features of modern file systems that exist. Basically, one of them is snapshots. This is extremely useful, and I think Windows has this enabled in a lot of Linux distributions. It does. Basically, if you have a problem with your computer, you can set up automatically, automatically set up snapshots. I am actually on a Windows machine here for the presentation, so let me check. If I type in a snapshot, I get nothing. So it's probably called something in Windows. But essentially, you can actually create an image, a full copy of your file system. It's read-only, so it can be modified. And if you run into a problem, you can just back up, reload this file system. You're going to lose all files that don't exist, but that have been created since. But sometimes it can save you a lot of time in your setup. For example, I have a prepared snapshot for my standard Linux environment, so I don't have to download and modify everything and download all the software that I need if I want to install my Linux environment anew. I can just or on a new machine, I can just pop that in, and then it just loads the snapshot that I have. Another example is compression, right? Basically, compression algorithms take your whatever file it is and encode it in a way that reduces storage space, right? If one way to illustrate it is, if you have a big number, a big number in binary, if you have something like 110 to decimal, you can, writing, a number like this. I posted in chat, writing it to decimal, you can actually write it in much, in less characters, right? That's one example of compression because, whichever file system this Microsoft Teams chat is using, it's storing those ones and zeros using the same amount of data as storing in 29354. So that's basically what compression does. It just converts encodes from one type of file to a different one type of written shape to a different type, and it can save a lot of space. One example is, if you have a lot of repeated values, if you have something that that you have, like 10 ones in a row, then you have 100 zeros in a row, it's much more compact to write 10, 1, 100, 0, and know that you're going to be able to recreate the original file from the compressed file because you're using some tricks. Or in music, for example, you can reduce storage by compressing files. If you're using MP3 songs that are which are the common format. M4A is the same thing more or less. It's a different container, but the same standard that YouTube Music uses M4A. That's why I'm mentioning it. And Spotify also uses M4A, I think. It's basically compressed format, and it's compressed by removing any data that describes frequencies that are higher than 18,000 kilohertz and lower than 5 hertz or something like that. It depends on the level of compression that you're doing. Why? Because you can't hear, because most people can't hear the difference, can't hear those frequencies, right? For example, FLAC is an uncompressed data music format, while MP3 is compressed, and it chooses that by deleting those frequencies that most people can hear. This is why some people, when you're listening to YouTube Music versus a CD, you can hear a bit of a difference because CD is uncompressed, and that's why some people prefer listening to music from CD players or what do you call them in English? LPs or the gramophones. Uh, because they can hear those frequencies that are removed with digital playback, some forms of digital playback. And some file systems will perform that sort of operations automatically, especially on data that is not commonly accessed, because obviously when you compress something, you need to decompress it. You can think of it like using WinRAR. 7-zip or zip files in general are an example of compression that you may have used. So you don't want to keep all of your files within a RAR file or a zip file and unzip it every time, but for example, using journaling, your file systems can check like, oh, hey, this file was accessed in a while. So to save space, I can just compress this bunch of files that have last been accessed, I don't know, 6 months ago. And because I'm assuming that my user is going to access them often. So if he needs to access them, or she, if they need access to these files, they can. I'm going to unzip them. They're going to wait for a moment until I give them the file because I need to decompress it. And I'm going to keep track. And if I notice that my user, for example, I don't know, maybe as a student, you're using Word a lot, Microsoft Office Word a lot, or PowerPoint, and it's going to say like, okay, so yeah, it hasn't used it since June, right? Because that's when the finals were. So I'm going to compress the files that allow my user to access Microsoft Office, right? And it's going to use less space. And then and in return, when my user accesses it again in October, when when it starts, it's going to be a bit slower. But I'm going to figure out that hey, my user has accessed this PowerPoint. It has opened it like 5 times in the last 10 days. It's obviously not something that needs to be compressed because it's unused anymore. It's going to decompress it, and so a lot of systems use this, do this compression and detection of what needs to be compressed automatically based on your journal. So yeah, journaling is pretty important in modern file systems. It enables a lot of stuff, although it creates a bit of overhead. So overhead means that there's more operations that need to be completed, right? Because you need to write to the journal and check it, and it takes up a bit of space, but not a lot of space, right? You don't need a lot of space. It's essentially a text file. Uh, Another example is the duplication, where, for example, this doesn't mean just deleting files, right? This means detecting that there's a duplicate file and then deleting one, but in a way that you won't necessarily notice, right? So, for example, if I have this presentation that I'm showing, I have it in my documents and I have it on my desktop. A file system with the duplication is going to simply do, okay, both of these files exist. I'm going to save their inode, but instead of both of them having their separate data blocks which store the same data, I'm going to modify one of those inodes so it points to a different set of data blocks, right? So it's just creating a pointer that points to, a certain area of space, which is the data, and then the other data can be used. And because me as a, as a user, I don't see on a modern operating system where that data is stored. When I click it, when I click, my data management .pdf, I don't care if it loads it from a different location where I originally put it on. So it's going to automatically deduplicate it by modifying inodes, and that's a very cool feature that allows you to save a lot of space in certain operations. And obviously, supporting large file sizes and storage capacities might seem banal, but it's not. A lot of, I remember when file systems wouldn't support more than you couldn't have more than 4 GB of RAM right on older Windows because it simply didn't support it. It couldn't allocate a RAM of that size, and you couldn't have a terabyte size drive because Windows XP in that period, people didn't expect that you could have that big of a drive as a personal user for the lifetime of Windows XP, right? So, and adding them isn't as simple as you would expect, because some schemas, some algorithms that you may be using, like FAT allocation table, like FAT file allocation table, don't work great with large file sizes and storage capacities. Because an extremely large file allocation table is going to take a lot of time to search, yada yada yada, and creating specific algorithms that support larger file sizes and storage capacities are, it's important to actually enable usage of larger file systems, especially today when we are talking about relatively small organizations using petabytes of storage. I don't know if you like computers, you're interested. On YouTube, you can check out Linus Tech Tips YouTube channel. It's a YouTube channel, right? And it's a small organization. They need a petabyte level storage, simply for backups of their videos, right? That's the world we live in today, where a relatively small organization, a YouTube channel needs petabytes of data. So it's not, it's actually, in programming, a very popular position, and you can earn a lot of money if you're very smart about manipulating data. So let's just conclude for today. So, as I mentioned, file systems are essential for data organization management. It's what allows you, and when I say you, I don't mean just you physically behind the keyboard and the mouse, but the programs that you write. It allows you to manipulate files, right? As I said, if you're in Python, if you open a file, you don't have to you don't have to worry about where you're writing the data. You just have to create the file and call it a day. So that's extremely useful because it creates an abstraction layer that simplifies your life a lot. Different file systems will cater to different needs, same as storage, same as it's same as the storage media that we talked about before. A lot of file systems, because it's simple to create new file system. You can there are some classes, some universities that deal with creation of file systems. You can create a file system in a week. There are a lot of different file systems for very narrow specific usages, much more than the different data media types, hard disk drives, SSDs, etc., because it's much easier to create them. So it's if you are willing to optimize it, you can cherry pick a perfect file system for your application, or modify an personal source one to fit your needs. This isn't usually necessary. It can be a lot of effort for a little gain, but it's good to know what's available, right? Because sometimes that 1 or 2% is generally something that you're going to need, to improve the operations and optimize, speed up the system usage. And that's why knowing how file systems operate and what you can do to them is crucial. Especially if you're working as a system administrator or something like that, where you can know different performance, security features, reliability features of your systems, so you can know how to use them, what you can set up, and if the system that you're currently using is satisfying for you or not, right? Okay, so that's all for today. Next time I'm just going to roll back to the start. Next time we're going to cover most probably, I think tomorrow we have data visualization with colleagues from Kragujevac. So I think I'm going to see you on Wednesday, me or Professor Tsar, and we're going to discuss data redundancy, transfer protocols, and databases. That's at least the general plan for the next week, next lecture, not next week. So if you have any questions regarding this, let me just type in my address. So you can just message me here at this address, ask me any questions that you have or anything that you need. Or if you have any questions now while I'm doing this outro, feel free to raise your hand, turn on your microphone, ask it in chat. Don't worry about it. Again, feel free to interrupt me. All in all, I know it's a bit of a boring. What did I? Oh, I know it's a bit of a boring topic. Data management and files, but it's a pretty useful thing to know when you're dealing with computers, because finding out that there are a lot of things that if you want to do some lower level programming, that this stuff is super important, and I hope you will see some of it in following. Thank you for the comment. So yeah, thank you very much. See you Wednesday, and I hope I wasn't way too boring. Goodbye.
Excuse me, can I ask something?
Yes, go ahead.
I just want, it's something about like how the classes work. So before the whole thing started, we were sent an email where it asked us what classes we're interested in, and I just wanted to ask if we're allowed to join other classes as well. For example, I personally have more interest except for the lessons I've already assigned. So I just wanted to ask if we're able to join more than the classes we've filled out.
Yes,
That's all.
you can join. That's why we shared the links for all lectures. You can join any class that you want. It's essentially some classes, for example, this one won't, but for example, social aspects of AI will require you to like write a 2-page essay or something to complete, and basically you will need to listen to at least 4 classes to to get the certification at the end. But you can listen to every class if you want. That's why we try to not have any overlap between classes. And if you want to, like, if anyone wants to change like the 4 classes they picked, all right, you can just email at that basic. But you can listen to any class that you want. You don't have to worry about it.
All right. Thank you very much.
No problem.
And thank you for the lecture as well. It was very interesting.
Thank you. Thank you.
Excuse me, can you say again, what did you say about the social aspect of AI?
Yes. So I was just using it as example. Some of the classes might give you like a small task at the end or something like that. Nothing like an exam or something like that. For example, in social aspects of AI, you will have to like write a short seminar at the end. I don't know what other professors are going to prepare, but yeah, some classes might have something like that. I was just mentioning it.
Okay, understand. Thank you so much.
You don't, if you enrolled in social aspects of AI, you don't have to be scared. That's a very simple class. So
Okay.
okay, any other questions? I say that okay. Thank you everyone for who wrote in the chat. If anyone has any questions, feel free to ask. If not, I'm going to end the lecture and take care of the video and the other stuff.
All right. Thank you very much for the lecture. Have a great night.
Have a great
Good
night as
night
well.
to all of you. Good night. Bye.
Good night.
Good night.
Bye.
Bye.
Thank you very much. Good night.